Hopefully you can all hear the microphone and looks like we're going live successfully. Cool. Okay, QR code is here for those of you in person. If you're watching the recording or joining live online, also hello. Can I get someone in person that may or may not be named Alex to check the stream to make sure it's okay? The other Alex. Please scan the QR code if you're in person. Yeah, so welcome to the CPMSoc and MathSoc 3711 Revision Seminar. We'll be walking through the whole course today, so shouldn't take the full 4 hours, but we'll be going at a reasonable pace. We won't be going through every single bit of the course, but the main things that we think are important and some relevant examples. There is also our study session tomorrow, if you want to go to that as well for some more practice and more board tutorial type engagement, whereas it's going to be more lecture-led. If you have any questions at any time regarding the content or anything we're going through, or like the occasional mistake, particularly by me, feel free to yell at me and let me know, or ask me questions if I say something that I should elaborate on. So I will be presenting the first two topics, first two quarters of the course, so that making the first half of the course, the group theory half. We had someone else who can't make it today, unfortunately, who worked on the slides for the first quarter of this seminar. Unfortunately, they couldn't make it today to present that, but I'll be presenting for them with some modifications I made last night. And then I'll be presenting the second quarter, which goes on from group actions. So I'll be covering, sorry? Shout out to Justin, yeah, my goat. We love Justin. Wait, why can't I? Yeah, smiley face for Justin. Okay. Right, so if you haven't already, please scan the QR code. And is everything okay with the stream, Mr. Alex? Can Daniel check or Jeff check it? Oh, and Jeff, can you check the stream? Daniel, can you check the stream? Okay, okay. Is the audio okay? Okay, cool. I- Let's see if I can. I'll turn up the hand. Like if I say this, that's lower, and that's louder, is it? It should. I've turned up the handheld um, audio in the system. So let's see if that works. Okay, so as I said, I'll be going through group theory in its entirety in roughly 1 hour and 40 minutes. It shouldn't take too long. So I'm sure you all were very comfortable with group theory leading up to your midterm before, but if you're like me and remember the fact that it's been 4 weeks and a little bit since the midterm, you may have forgotten a few things that we want to make precise again and get into that same state of knowledge that we want for the final exam. So we're going to be revising from the fundamentals of group theory to try and get back into that state. So you should all remember what the definition of a group is. You have this binary relation that implicitly has this closure. So you have this operation you can write as a little star from takes two elements and maps to another element. So you have closure under this multiplication map implicitly by it being a well-defined function. And then you have the other three axioms, properties that you need the group to satisfy: your associativity, your existence of inverses, and existence of identity. Okay, and then I'm sure you remember the definitions of abelian and the order of the group. So the order is the size of the group. You say that's the cardinality of G if it's finite, otherwise it's an infinite group. And abelian means that the multiplication, you can swap the order that we're in. Okay, and then subgroups, you may not think subgroups are too important. Once we learn about normal subgroups are really the important ones. Subgroups themselves may show up in certain contexts. They are just subsets of your group such that they have an induced kind of group in and of itself by closure onto multiplication, and also has all the relevant inverses. So it has all the relevant information within that subset for it to form a group. Okay, so you restrict it to that subset H. Okay, yeah, and it contains the identity. So if for some reason this shows up in an exam question, remember to check those three things. It contains the identity, closure under multiplication, and contains inverses. Okay. I don't know, why is there another slide here? Okay. Right. So the order of an element in contrast to the order of the group is just the smallest power of that element, the smallest n, such that you get the identity when you raise the element g to that power. That's very important to us. So say, for instance, in cyclic groups, instead of a z, nz, your if you look at z over pz, then you could say the element has elements of order p and 1, for instance. So if you take a non-identity element, then it has order p. If you take the identity, it has order 1. And then you could have examples like this. The integers themselves have infinite order. And related to that, we can also talk about group generators, generating a group from just the set X and contained in your group. What you do is you can generate a group by taking all the relevant multiplication and inverses. So if you write S inverse for the set of inverses relevant to your set S, which you're trying to generate the group by, if you take any relevant product in any type of order like this, you can get your group. And equivalently, and this also shows up when you're talking about when you come to ideas later in a different context, you can frame it as the smaller subgroup containing S in the sense that it's the intersection of all subgroups that contain S, which forms a well-defined group that we call the generated group. And it's finally generated when this set S is going to be finite. Okay. So this is one of the more straightforward type questions you may see in an exam where you're given some quite abstract but somewhat interesting operation, and you're asked to show that this is a group. So briefly, just to revise on this, what we can just do is check the three properties. First of all, that this is a well-defined action comes from the fact that we're taking this existing group element and we're forming this multiplication from the existing group multiplication. So this is a well-defined map from G times G. So this circle goes from G times G to G. That's well-defined. We want to check associativity, existence of inverses and identity. So I'll do it in that order. So for associativity, I'm just going to write what we need to show is that a circle B, circle C is equal to a circle B of C. But without going into full detail, you can hopefully see that both of these would be equal to a U inverse B, U inverse times C. And you follow from the associativity of G to get you the result. The second condition, let's say, has the identity element. In this case would be, right, as E is going to be equal to, let's say E under G circle is equal to, it seems U. We can check, for instance, that a circle U is equal to a U inverse U, which is equal to A, so it satisfies the properties that we want, and we can do it that on the other side to get U circle A equal to U as well. So that would be our identity, so just watch out for those types of properties, thinking abstractly. And then finally, inverse, so we could say inverse of an element A would be, and it may take you a bit of time, but I remember the answer in this case would be U times A inverse times U. So we can check that. All we want to make sure is that the inverse of A, so we want to check that UA inverse U, circle A, we want this to be equal to U, the identity, and you can verify that that is in fact true. And likewise, A circle U, A inverse U is also equal to U. So pretty simple. Okay. So we can write out the steps there. You can see all the details, and that's all you really need to show. Okay, so we're just remembering how to build from our fundamentals here. We'll get into more complicated questions later, but remember, the exam will still ask on maybe simpler questions like this. The next question that we have, again, you can pretty much one-shot this if you remember pretty much anything about cosets, but we want to prove this one from fundamentals. What we're given is a group, and we're looking at a subgroup H, where we're told it contains every element within our group except for this one element G. We want to show that the size of the group can only be 2. So you can think about this in terms of Lagrange's theorem and so forth. Again, not looking at that for now. We'll just try to prove it directly, just to redevelop that intuition and what we were doing in week 1 and week 2 when we were trying to prove results directly. I guess in the earlier weeks there were some results as well that we could have one-shotted if we knew the Sylow theorems, but remember the troubles you went through when you didn't know those. So in this case, we have to do something. We have to play around with what we know. We know that H is a subgroup, which means we have to have such things as closure under multiplication. So what we can think about is H would contain an element. So let's take, and we want to show that element, if G is of size 2, it suffices to show that H only contains the identity. We'll come back to that idea. But we're going to take H, little h in H. That's well defined. H is non-empty. And we consider G times H. Okay. So consider G times H, and let's call this, what's another? H dash. If H dash, so this one case, either H dash is equal to this G or H dash is in H itself. If H dash is in H, that implies that G, which is equal to H dash times H inverse, is also in H. But this is a contradiction, but that is not true. So that implies that GH is in G set minus H, or in other words, this set G. So it's GH is equal to G, which if you remember, one of the key properties that you have in groups is this cancellation, where this means that H is equal to this identity element. So H is equal to 1, and since we took any arbitrary element H within our subgroup H, this shows that that element has to be the identity, and we will just write this as identity, which means that H can only be the identity element, G would be another element, and so you have only a group of size 2 in total. Any questions on this? Sleep that up if you want to take notes. I guess you can frame it like this as a similar way to do it. Okay, we'll move on. Yeah, so Justin wrote this slide. Here are some of his favorite groups. So these are some good ones to know and have in your back pocket in case you want to prove or disprove a result or try to interpret a question. Advice I've gotten from Dominic again and again is to always have examples to understand where your theorems work and where they don't work. And these are the types of examples that you should go to when you're looking at trying to come up with counterexamples to questions, say true or false questions, particularly when you're trying to come up with non-abelian groups. These three that we have here, dihedral, symmetric, and antisymmetric, are quite important. In terms of abelian groups, you have the classical addition groups, and then you can have the multiplication groups for the rational numbers R and C, but not Z because there's no inverses. So likewise, as I've written here, R cross is R without 0. And I suppose actually, I guess if you follow the notation closer to the later in the course when you look at rings, you could say that this is the group of Z with the group of units of Z, which are, I guess, cross is equal to 1 minus 1. So I guess it does. Z cross does form a group, just a very simple group. It's just of order 2. So maybe I'll fix that. Zn is an important one to know. The group of integers between 0 and n minus 1 under addition mod n. And then you can think about doing interesting things with different rings and different matrices, polynomials. You can create matrices with the elements being elements of a ring and consider, what did I say, matrix multiplication there? It should not be matrix multiplication, addition. Okay. Yeah, it should be matrix addition. You can do a similar thing with polynomials. Dihedral, symmetric, anti-symmetric, we'll get to in the next slide. And then you also have the trivial group with just one element. Okay. And you can also take different products, direct products, and quotients of these groups to get more interesting ones. For instance, you could take a quotient between, in the dihedral group with a subgroup, a cyclic subgroup generated by sigma or sigma squared or something. Okay, so I won't gloss too much on the symmetric group or dihedral group. I'll just remind you with what you should revise on if you want to get very precise for the exam in terms of the notation and terminology that has shown up in some lectures. So remember, there were some lectures that Alex gave that go over details in terms of the sign function and so forth within the symmetric group, and hope you all remember his little visual aid of his hexagon when he was talking about the dihedral group of size 6 that linked the dihedral group to the set of symmetries at the end of. So this slide is just telling you to revise those if you haven't already. Symmetric being the permutations on a finite set of size n. You should know and love these two groups very well, but I understand it's been a while since we might have looked at them, given group theory was a long time ago. And as I said, the sign, you can know, you hopefully have this very engraved intuitive understanding of what it is when you say that the alternating group is where you have the sign is even, the parity is even, you have that produced from an even number of transpositions. So if you express any permutation within your symmetric group, then the number of transpositions you can write that permutation as is always going to have the same parity. It's always going to be either an even number of permutations no matter how you write it, or it's going to be an odd number of permutations. And so we can have this well-defined sign function that is multiplicative in this way. And you can use that to generalize. But yeah, intuitively, you can just think of this alternating group. I said anti-symmetric for some reason before. Alternating group as where there's an even number of permutations. So your, say, 3 cycles and so forth, but not your 2 cycles, not your transpositions. Those have odd parity. Okay. Yeah, and this is the reason why it forms a subgroup. So anti-symmetric is, well, in fact, a normal subgroup because it has index 2. We'll revise that. Yeah, we have index on this slide. So remember, we can do cosets even if we don't have a normal group. So Lagrange's theorem applies to any subgroup H. In fact, what you can do is look at the cosets. So what happens when you multiply every element in H by a fixed element G in your group? You get not a subgroup, but a set of elements, GH, of the same size. You can think of it as a function mapping from H to GH. That is 1 to 1 and on to. And what happens if you're dealing with finite groups is we have this very powerful and useful theorem by Lagrange, which hopefully you have this intuition, but just to state it precisely, is it says that what you call the index, which is the size, the number, which you say the set of cosets. So this isn't the quotient group just yet because we don't necessarily have a normal group, but the set of cosets, each of these, where you don't like take the duplicates, the number of those is equal to the quotient of the size of G over the size of H, and since it has to be an integer belonging into a coset is an equivalence relation, it partitions your space into equal size cosets. The result, the usefulness of Lagrange's theorem that we've been using this whole course is that the size of any subgroup divides the size of the order of your group. I should be saying order. Okay, and you can also define interesting things like product of two cosets of subgroups. And an example to be notationally aware is you can write your cosets of mz, the multiples of m within the integers, as these like equivalence classes where you put the little bar on top to be precise, is the way we do it in the course. To say that the remainder, I guess when you divide by m, is this number, the set of remainders. Okay, so this is what we actually care about, our normal subgroups. So remember, there's a lot of different equivalent ways to write that a subgroup n is normal. You could say that if you take an element G, the left and right cosets are going to be the same. Another way to say it, so that's this first one, another way to say it is that when you conjugate that subgroup n, conjugating a subgroup gives you another subgroup, but in this case, conjugating it gives you exactly the group itself. But you don't have to be that strict about it. You could just say that if you take any, what this really says is that G and G inverse is going to be within n for all n in n. G and G is what you only really need to say. Okay. So that it suffices to show that. So all these three are equivalent to say that we have a normal subgroup, and that induces your quotient group, G over n. G over n is a quotient group with multiplication being where you just multiply the two groups together. The identity is going to be n, so again, another thing to be notationally aware of, identity is n. And the inverse is you just take the inverse of the representative. So you really just work with the representatives of these quotient groups, the cosets, the G and the H, in this case the G, to get your products in terms of this quotient group. So that's to say, you kind of ignore n in a certain way. You just think about the representatives of each of the cosets. So you're, as Justin would say, and I would agree as well, this notation G over n, and I've heard Dominic say similar things. The way I read it is G modulo n, to say you're sucking out the information encoded within n into G. So all you care about is, you don't care about elements that differ by some element in n, you can kind of think of, the remainder being n in a certain way, multiplication by an element in n. All you care about is their structures beyond that, you're sucking out the information. Okay, so we have groups all set up now. What we care about more than just groups themselves is how groups interact and how we can have morphisms between them. So you may have forgotten what a monomorphism or epimorphism is. The way I remember it is that those are two words, and one of them means injective, so the other one has to mean surjective. I guess easy to remember that mono means injective, like one-to-one kind of. I hope you know what isomorphism means. If you don't, you might have troubles. And surjective is the other word that may appear. So epimorphism, not that we use it much. The idea of a homomorphism, we should all be familiar with, it preserves the structure in a certain sense in G within H. So you preserve what you care about, which is the group multiplication structure. So if you take the product of two elements, the image is the product of the images. And you can get precise. What motivates the first isomorphism theorem is that this idea of replicating a part of G and H is that when you don't have that the map is injective, you kind of have elements squished to the same part of H. So if you kind of suck that out, then you can see exactly what that image is isomorphic to. But we'll get to that when we look at the first isomorphism theorem. Kernel in an image are also very important. So kernel is the inverse image of phi of the identity element, which forms a normal subgroup. In fact, if you take phi inverse of n and normal in H, if we're mapping from G to H, this is also normal. So you're saying if you take the pre-image of the trivial normal subgroup, the identity subgroup, then that's what's going to be normal within G. So there's this nice relationship that Justin likes to talk about between normal subgroups and the kernel of isomorphisms. And you could also talk about the image, which is just everything you get out. So the only part of H that's relevant with respect to this isomorphism that you're using is what the image is. Let's move on. Okay, so I have this little question. It's a bit of an esoteric question. I put it in here just for the, I guess, novelty of it compared to some of the things we've done in board tutorials. So that's to say it's a bit different and the work that we've done so far. We're going to try to play around with the definitions of this homomorphism. So be cautious of what we're looking at here. We're looking at a sum of the image of every element under a homomorphism phi. Notice though that we're mapping from a group G to, that's I believe they say finite. So finite's important, meaning that just a finite sum. But we're taking addition here. So since we're taking addition, we just have to be cautious. We're mapping to C, let's call it Cx instead. Cx, which is every element in the complex numbers except for x. And the reason why we write it like that is because we're looking at the multiplication group instead of addition. But I guess because the complex numbers also have inherently built into them this addition structure, we are taking then this sum of all these. Okay. So what we're told in the question is that this homomorphism is non-trivial. Non-trivial means that there exists some h in G such that phi of h is not equal to the identity. So we're going to use that in some sort of way. We're going to play around with this idea of cosets here. So let's write out what this sum is. So we're looking at this sum. I'm going to define it as S, this sum over the elements of G of their image, phi of G. But for the same way, when we talked about cosets, that when you multiply on the left by an element, you get out another, I guess, not a subgroup, but another coset of the same size. That is, here, what I'm trying to say is that if you look at this instead as h times g for g and g, this would also be going through all the elements of G. You can just write any element with multiply on the left by, I guess, H inverse, and you can write it in this way in a certain sense. I'm just going to say, wait, I'll write it like this. Maybe it's better. That's to say, G, that's the way you would say it, because all the cosets are of the same size, and the only coset that we're working with is the kind of trivial coset, not because it's empty, because it's the whole group. So when you multiply it by h, you also get the whole group. Okay, so what we're going to write this as, I didn't mean to write that, gh, and since we have this multiplicative structure in the homomorphism, we can write this as phi of h times phi of g. And the reason why we do that is so we can suck out this phi of h from the sum. It's a finite sum. We don't have to worry about convergence or anything. G, and I'm just going to write this as g and g, phi of g. But this sum here is exactly what we started with. And so phi of h times s, what we have is that s is equal to phi of h times s. And hopefully you can see what happens from here, because we are saying that phi of h is not equal to 1. But I guess if you love your ring theory a bit too much, you could say, in other words, you have this product that is equal to 0, and you're working in an integral domain of the complex numbers. So one of these has to be equal to 0. So s is equal to 0, or 1 minus phi of h is equal to 0, but like that can't be equal to 0, so we're doing this one, s is equal to 0. That's what we want. Beautiful. Okay, so a bit overkill, but that gives you the result. And yeah, it's a little interesting question. Okay, so some definitions to remember. I put in this slide for no particular reason, but they come up in use later on in the course. Automorphisms is the other of the actually there's two words here. Automorphisms is our fourth type of morphism where you're mapping from your group to itself, and it's isomorphism. It's called inner if it's some sort of conjugation. The map is a conjugation map. So that's interesting. We have a little question on that during the break, hopefully. And then just two pieces of definitions that will come up useful in group actions is the normalizer of a subgroup H, which intuitively says it's every element in your group that, I guess, commutes with the left coset is equal to the right coset. In other words, that when you conjugate H by this element, it's equal to H. So it's a certain sense of normality. So that's to say that H is a normal subgroup of normalizer G of H, and you can get precise. It's kind of like the largest subgroup such that happens in a certain sense. Finally, we have the center, which is the set of elements in your group that commute with every single other element. Again, this will come up in use within our study of group actions. You can think of this as the, in the context of the conjugation group action. Because it's just saying that it's a set of elements G such that GH H inverse is equal to G. So that set of elements that stay put when they're conjugated by every single other element. Okay. So I put this slide here to remind you of the notation that Alex often uses in lectures. So it might be in good interest to remember this when you want to be precise. So there is the quotient morphism, which is also used a little bit in the notes in terms of, it shows up quite a bit when you look at the proofs of the different isomorphism theorems, and also in the way that Alex approached the proofs in his slides. Really just mapping from G to the quotient group by the simple, you take G, you map it to G times N. And then the inclusion map when you map from a subgroup to the group itself, not particularly important, but it just keeping the element the same. Just important to be aware of this type of notation and concepts. And if you love to use your words of epimorphisms and morphisms, this second map is a epimorphism. The second map is a monomorphism. The first map is an epimorphism. If you love those words. Okay, right, so as I said, this is one of Justin's favorite, I guess, results or favorite ways to interpret normal subgroups. Where does it say every subgroup? Oh yeah, okay. I guess you can make this a stronger claim if you wanted to. I said normal subgroups because in abelian groups, you may remember every subgroup is normal. But let's try to prove different version of this question. You can see like the simple case here. Let G be a group. Show that every normal subgroup of G is the kernel of homomorphism from G. So first of all, what we can show is that one direction is that if phi is a homo, and we write it the full word, then kernel phi is a normal subgroup, or I should say kernel phi is normal in G, since we can write if G is in G and N is in the kernel of phi, then we can look at phi of G and G inverse. Well, we want to show that G and G inverse, to show G and G inverse is going to be equal, in the kernel phi. So what we can really just consider is if we take the image of G and G inverse, we want to show that this maps to the identity, but we can use the multiplicative nature to write this as phi of G, phi of N, phi of G inverse. And phi of N is 1, so this is phi of G times the identity, 1 times phi of G inverse. This becomes phi of G times phi of G inverse, and I guess this proves another property that we often use just because it's intuitive, that this becomes, again, the identity. In other words, that the inverse of phi of g is equal to phi of g inverse. That is shown by this. And so we have that the kernel of homomorphism is a normal subgroup. And for the other direction, we want to show let n be normal in G. We want to show n is the kernel of some phi. I'm going to make phi the most natural choice would be something involving n. So that's kind of like when you're thinking about what your group action should be when you're approaching a question like that. You think about what should my isomorphism be? It would have to involve n in some sort of way. In fact, what I'm going to do is map from, let's say, which one should I have it in? G to G mod n. And we can think about why this makes sense, because if we take any element in n, then it maps to n itself, n times n, little n times n, still n. And I think that should be enough. So let's just check this. If, let's say, G is in kernel of phi, then, oh, I should give the specification. Phi of G is equal to Gn. And maybe I'll write it like this in the interest of time. This is equivalent to saying that Gn is equal to the identity of G over n, which is equal to n. That is, G is in n, as we talked about before. And that's really all we need. So that would be to say that kernel of phi is equal to n as we want, and so we pretty much have the result here. Okay, and you can see that it's basically the same as what has been said here in the case of an abelian group when you're talking about subgroups, because in an abelian group, every subgroup is normal. Okay, so here we have our isomorphism theorems. We'll just draw them out. Have them all laid out. So as I said, first isomorphism theorem, if you don't know that by now, you should be very scared. If you suck out the information of what the kernel is saying, you get this induced, I guess you could say you have this induced phi tilde from G over the kernel to image of phi that's injective and surjective. So it's isomorphism. So if you suck out the information given by the kernel, everything that kind of maps in that remainder, so you modulate by the kernel, the structure that's preserved within your quotient group is what's in the image of the isomorphism, so that's what we care about. So the first isomorphism theorem is used to prove the next two, and it's really the most important one, but there are examples where the other two do show up and are quite important to still be considerate of. The second isomorphism theorem, the statement you should at least algebraically remember by now in terms of have some sort of visual image of what this looks like in terms of your interpretation of it. I think Alex is from the lecture of the diamond, what's commonly called the diamond isomorphism theorem, is not a bad one. We draw a diamond like this, H and N. So you have normal here, and you have normal here. Not a bad way to think about it. Intuitively, I can't give much help. The third one is a bit more intuitive, at least to me, because, well, algebraically you can cross out the n's and ignore they exist. But really what you're saying is that if in both cases in G and H you suck out the information from n, then you kind of, then you quotient them is equivalent to just sucking out the information from H. So like the net result cancels out, which is the algebraically similar case. And yeah, the third isomorphism theorem is commonly thought of as like another part of the fourth isomorphism theorem, which is the important part really is that you have this correspondence, this bijection between the subgroups of G that contain H and the subgroups of G modulo H, because you can kind of think of, say for instance, in G modulo H, the identity subgroup is just the element H itself, the identity, whereas in terms of the subgroups of G that contain H, the most simple one that you can have is just H itself. And yeah, this bijection preserves normal subgroups. It's kind of the third isomorphism theorem implicitly tells you in a certain way. So that's to say if H is normal in G, then H modulo N is normal in G modulo N. Okay, so we have some actually not too bad questions on these. For this first one, we're given these two cyclic groups, so Z modulo MZ and Z modulo NZ, and we're asked to show that there is no non-trivial homomorphism between these two groups. So of course there's this trivial homomorphism that maps every element in Z modulo MZ to the identity. We want to show that there's more than just, there's no more than just that, using the fact that M and N are co-prime, so there's no common divisors of them. So let's think about what we can do. So the obvious proof would be to, not obvious, but the first thing I would try to look at, the really only thing that you can look at is, say there is some sort of homomorphism, what can we deduce based off the sizes of elements? So when we're dealing with the isomorphism theorems, they're particularly useful when we're talking about the sizes of different groups and how they relate. So let's look at this. So if phi is from Z modulo MZ to Z modulo NZ, then what we would have to have is by first iso, we would have to have that Z modulo MZ over the size of the kernel of phi, just by Lagrange's theorem, and I should say Lagrange. This would be equal to the image of phi, and by Lagrange's theorem, this divides the size of Z modulo MZ. In other words, this is saying that N over the size of the kernel of phi divides M. So that's the saying a divisor, because the kernel of phi has to divide N. A divisor of N is dividing M, but we know that the largest number that divides both of them is 1. And so what we have to say is that this means that this number has to be 1. That implies kernel of phi is equal to N. And so looking at the orders, we're dealing with finite groups. This means that the kernel of phi is equal to Z over NZ, which is the entire group. That's why we would say it's trivial. It's a trivial homomorphism because it just takes the whole group and maps it to the identity. It doesn't do anything in particularly interesting. So you can see this is making the same argument as we are here. So you look at the image divides the sides of the group H. The image is always a subgroup. We haven't covered that, but that's another property we should all know and love. Okay, any questions on any of these previous examples? Cool beans. All right, let's move on. So you may notice that this question is a bit contrived in how it's stated, because it's not too easy often to make a question that asks about one of the isomorphism theorems that isn't the first one, but we'll make do here. So this is actually relatively interesting though. We're given this normal subgroup of the general linear group over C, which has scalar multiples of the identity matrix, and what we want to look at is the special linear group over C. We want to find a quotient group of it, so a quotient of special linear group over C and a normal subgroup of it. We want to find one such that it's isomorphic to the general linear group over C modulo N. Okay, so this in this example, 3 groups that we want to look at. There's N, SLN, C, and GLN, C. So that makes it a relatively good candidate for either the second or the third isomorphism theorem. And so if we want to find just a quotient, though, of the special linear group, on this left-hand side, all we really need is just one quotient. We don't really need this whole quotient of quotients that the third isomorphism theorem gives. So what I'm going to use is the second isomorphism theorem. Even I just did not remember which one it was called. But we're going to try and say that this will look like, since it's modular n, we want this kind of to look like hn modular n. Just a little side note is that, remember that hn equals nh when n is normal. So it doesn't really matter which way I write it. So I believe Alex has written it in the other direction as to the way we wrote it in these slides. Doesn't really matter. We want G to be looking like, what was it? H over H intersection n. Okay. So we would like H times n to be equal to the general linear group over C. So let's hope that that is true. What this is, H times n, I guess we're forced to make H as SLN n C times this n, this n here. So what this kind of intuitively says, record that SLN C is a set of matrices such that the determinant of the matrix is 1. Let's see. 1. And I'll hand wave a little bit for the sake of time. What this is basically saying is we're taking some matrix, all the different types of matrices we've determined at 1, and we'll multiply them with all the possible scalars we could have in C for that, and that's basically going to give us all possible different matrices, then allowing that to be stretched out to all the different determinants. So we're just going to hand wave this and focus on the interesting part of the question, which is now we have H identified as our SLN C. We want to find this quotient. So really the part of the question that's interesting is finding what H intersection n is. So that's SLN C intersected with this n here. So that would be is lambda times the identity such that the determinant of this lambda times the identity is equal to 1. But since lambda times the identity, we're working in C to the n, the determinant of this matrix with lambda on the diagonals is lambda to the n. So we need lambda to the n equals to 1. In other words, lambda is a nth root of unity. And so that's really what the question boils down to. We are dealing with H intersection n, which is normal in H. H intersection n is going to be equal to, let's say, W omega times I, such that W is an nth root of unity, which forms another normal subgroup. And by the, was it second or third? I always forget. By the 2.5th isomorphism theorem, that means that our quotient is going to be epsilon n over these identity matrix times the roots of unity. Okay, any concerns yet? All right, so we'll briefly walk over this chapter, mainly having it here for, again, just to remind you of the notation involved in all of this. So you've been working with products and sums of groups from week 3 onwards and never really maybe looked back into the precise formulations, and we won't be looking into too much detail on that really here even, but I'm just reminding you that that is something you should look at beyond what just we stated in the slides. So first of all, we have what's called the external direct product, which is what happens when you kind of consider your groups, you have G1 to Gn, you consider them as, you put them together as a sort of vector where you take element-wise multiplication or element-wise group action. For instance, R cross with R cross, first component is element from R cross, second is also from R cross. You can do something like this. You multiply coordinate-wise. Okay, and you can do some, I guess, more interesting examples, such as if you have, what's everyone's favorite group? Let's try D, like Dn together with Z over Nz together with, say, in this group, together with, what's another group we care about? So the complex numbers under multiplication. Then we could have, let's say, sigma and then 2 and I multiplied by, I'm just going to write this dot for multiplication. I could do this, say, tau sigma mod, and then let's do n minus 1. Let's do 2i. Then this would be equal to sigma tau sigma, which is, should bring the tau sigma inverse. Yeah. That's right, isn't it? And correct me if I'm blundering this. 1 and then C star is multiplicative, so you do negative 2. Okay. Yeah, because remember the dihedral group, unless I'm actually throwing sigma tau is equal to sigma inverse tau, so that makes sense. Okay, cool. So just some arbitrary example like that. You can see some on one lecture slides. That's your external direct product. Some other definitions that you should know. Your canonical injection and projection. So these are two maps that notationally you should be aware of. Again, canonical injection, you take this external direct product and you yoink out, sorry, canonical projection, you yoink out the element at the k coordinate for pi k. And if you love your words monomorphisms and epimorphisms, this would form an epimorphism. Whereas on the other hand, your canonical injection forms a monomorphism. You take an element from one of the groups and you yoink it into the relevant position together with identity elements for all the others. So that is a relatively, these two are relatively important maps if you know about something called universal properties, which I won't get into, that Dominic likes to talk about. Okay, so we have this little somewhat cute question here, which is saying, like with the third isomorphism theorem, can I just cross out the h's? So is this equal to, like, cross out the h's? Is g mod h, external product with h, just equal to g? So to spoil the answer, no, it's not. So one example that we could use is, maybe my go-to might be, if I look at something like this, one argument I might want to make is talking about the orders of particular elements. Let's try, since I'm dealing with external product, direct product, might try to show, shove in an element of finite order. If I make, say, in my coordinates of my external direct product, look at the identity in one position and not identity in another. In other words, I'm going to set G is equal to the set of integers, which has only one element of finite order, which is the identity, which just has order 1. And I'm going to make H, what's everyone's favorite number? We've used 6, 7 too much, so I'm just going to do a normal 1. I'm going to do like this. Let's say n is greater than 2, greater than equal to z. This has, say, for instance, the element 1, comma, actually, I just need to check something up here. Yeah, that's fine. Okay. 1, comma, what am I going to put here? Let's say 0 has order n, whereas n greater than equal to 2, whereas z has no elements of order n. Okay, and it's written very similarly here. You can take the same thing. Oh yeah, and I've been kind of abusing notation. I really should write either 1 with a little bar on top, 0, or to be precise in a better way, 1 plus n and z, 0, to be more precise about the cosets we're dealing with. To not abuse notation, think about mod n. Okay. But something you can prove if you just really apply the first isomorphism theorem with your canonical injection, for instance, you can prove this result that if you do take some sort of external direct product with just the trivial group in H, then that quotient does produce G itself. So you can get back out G if you do it like this. So you have that correct structure, whereas this is not true. So this is true, this is not true. Okay, right, so given we've talked about the external direct product, you may have also forgotten about the internal direct product in contrast to the external direct product. These are really you can think of them in kind of the same way, but we kind of formulate them differently. So instead of formulating them as vectors, different components, we can kind of think of it as the product of just like a formal expression, or just writing it as a group itself with products of elements, kind of losing the vector notation. The way you can say that is, this is the case where you don't necessarily have a billion elements, but what you do need to say is that you have this sort of linear independence condition and commutativity between elements between these different groups, G1 to Gn, which you're taking the product of, and no element can be written as a product of other elements in the other groups besides itself, is what this condition is saying. And so basically what that means is that we have this internal direct product, okay? And you may know it by kind of a more common name. So we'll come back to that. Common name when we're dealing with an abelian group. So when the group that we're dealing with is abelian, then we call this internal direct product the direct sum of subgroups. Okay, and you can have that condition that we talked about before. Equivalent to this, you have a sort of linear independence. You can express no element from one of them as a element from the other subgroups. Okay, and of course, like the first condition, the commutativity comes straight away between the subgroups. Okay, so this is really what we care about, the direct sum of subgroups, and then when we talk about direct products, really mean the external direct product in a certain sense. And you may remember the difference between those two themselves is that in the finite case, they're really the same when you're dealing with abelian groups, that is, where we typically really only care about direct sums of abelian groups. But in the infinite case, you can have an infinite product, and so they would be different. Okay, and yeah, more details within the course notes. And just coming back to this, yeah, the direct, for the direct internal and external product, you can have this isomorphism between them that is a bijection. Okay, so you map your components and you just multiply them together. You squeeze them together. Okay, so last part on this first quarter of the course. I won't go into any of the proof or any of the related details, so I don't have 2 hours on hand. See the course notes maybe for a refresher of what the proof details were, in addition to Alex's lecture, a whole 1 hour lecture on the whole proof. But the result from it, and also the previous lecture that was focusing more on cyclic groups, which related some results we knew beforehand, but formulated them in terms of a group theory way, in terms of greatest common divisors and lowest common multiples in terms of cyclic groups. There's a nice way to think about cyclic groups is that they're all isomorphic to some sort of quotient group of Z. Okay, so you can have the infinite cyclic group just generated by the identity element being Z, and then the finite ones are generated of what can be thought of as this quotient group Z of nz. So maybe have a look at those lectures if you have time. And then the big theorem that we care about is the structure theorem for finite abelian groups. You should remember from class test 2. This is one way of writing it, that it's going to be the direct sum of all these different quotient groups, these different cyclic groups, which have sizes of prime powers, and this is unique octal reordering is something some people lost marks of in the first test. Okay, oh, sorry, second test, forgive me. Right, so we have this kind of trivial example. I won't go too much into it. It becomes an easy task in a certain sense now to figure out what all finite abelian groups look like. You take your size of your group, in this case 360, and you look at the prime factorization of it. In this case, 360 is to the power 3 times 3 squared times 5. And what you could say is that if you consider all the different ways of writing that in terms of its prime parts, then it gives you all the possible different finite abelian groups. So we won't go into the full details. I'm sure you're experienced with this, but examples such as the ones here. So in this case, we are kind of using the group case of the Chinese remainder theorem in the way we're expressing it. For instance, this is saying this first one is a way of writing this. Plus, we do use times, but again, in the finite case, direct sum is direct product. Z over 3 squared Z over 5Z. Okay, any questions on this? Otherwise, we'll move on to probably the most difficult part in the course, in my opinion. I think rings are interesting, very interesting, especially the last topic on field extensions, and that part of the course is quite cool. But I think this is really the first math course I've ever done where the first half of the course is harder than the second half of the course, especially when you get up to Sylow theorems. But there is a quite nice beauty in group actions, and what Alex always likes to say is that when we study groups, we're trying to talk about symmetries and how groups encode this intuitive notion of symmetry. Group actions let us understand that further in this way that we define it. So going back to basics of group actions, what a group action is we'll look at this notion of a G set, which is a set S, together with a map with respect to a group that we take one element from a group and an element from S, and we say that the group element acts on S, and in a certain sense, to produce another element in S. So it takes the action, which we denote as G acting on S. This way, you can think of in terms of the symmetry of G, it does something to the element of S. So say we won't go into this type of example today, but you can see examples in the board tutorials such as of relevant questions, such as the group of rotations of, say, an octagon acting on the set of vertices. Okay. The two properties we need to make sure we're always careful of is this, I wouldn't call it associativity, but this kind of analogous condition to associativity that says that if we take the action of G after we've done the action of H, it's the same as doing the action of the multiplication of G and H. Okay, so we have that type of associativity structure, and we need to make sure the identity leaves every single element fixed. Okay, so that's what we call a G set. And one of Justin's other favorite points to bring up is that this G set, this group action, can be thought of as a homomorphism from your group to the set of permutations of this G set S. You can think of that being defined. You're going from phi from G to perm S that has this phi of G at S equal to G dem S. So an exercise is to verify and accept or understand the fact that this is a valid homomorphism. So some examples of G sets that we should all know and love. We have the simple-ish example of just a group acting on itself under the regular multiplication. So replace the dot with the times. We also have the conjugation map, which comes in very important when we talk about the class equation and dealing with the sizes of groups we'll use later. And then another one that we could have is a group acting on its quotient group under, I guess, well, it doesn't necessarily have to be a quotient group, but group acting on the set of cosets under a set of cosets under a subgroup H, where the group action of the coset is to multiply the representative in this sort of similar way to the way you deal with normal subgroups, but not exactly. Okay. Right, and I think I might have put on the wrong side, but we have, yeah, well, another example of an action is the trivial action, which in the midterm you hopefully remembered, which is where you just say that the action does nothing in a certain sense. G acting on S just leaves S fixed. So this shouldn't be here, but that's an example, as it's not meant to be here in this point in the slides. Okay. Right, so G stable, not really a particularly important definition, but leads to orbits. G stable is you act on this subset of S, it leaves, it doesn't go out further. So the action, the geometrical interpretation doesn't go out further than what you had originally. And the orbits you can think of as the smallest G-stable subset that contain a particular element S. So in the geometric interpretation, it's everywhere you can get when you act on S by all the elements in G, because if you consider this associativity, it's that it's G-stable because everywhere you go, you then get back to some sort of place you were originally in within this orbit. And formally, you should remember that these orbits define an equivalence relation. If two elements are in the same orbit, they form a partition of your G set. They form, yep, your orbits form a partition of your G set, and they each have, then what that means is that all the orbits have the same size, but that's formulated in the orbit stabilizer theorem. It's just repeating what I just said. Let's just make sure. Yeah, they form a partition of the set. They're also disjoint, so you can think of the geometrical interpretation again, the disjoint places you can get to from one particular spot you're already in that type of symmetry. And yeah, for the second time in the course, we see this quotient, or this notation. So remember from the week 10 lectures, we also use that same E over F for the field extension of E, the field F. We also used it before with quotient groups. And here again, it means something different. Here it means the set of orbits of your set S under your action from G. So that notation is particularly annoying, but just remember, it only really shows up one other time in the slides. Two other definitions to be notationally aware. Faithful isn't too important, but it just means that your action is nice enough. It doesn't have anything silly going on where there is a group element that just keeps every element in the G set fixed. So faithful if this doesn't occur. But what we care about is transitive. A transitive action is one that only has one orbit, or as that's to say, the orbit of any element is the same size, that being the size of S. That is, the orbit is always S. A nice way to go about proving that you have a transitive action is to look at a nice element to deal with in your set S and showing that the orbit containing S is the whole G set. Okay, so in terms of talking about how, with respect to a particular group, how two G sets are the same, we have this notion of isomorphisms or morphisms between G sets that don't necessarily have to be isomorphic. But like with groups, we want to preserve a particular structure. In this case, the structure that we want to preserve between these G sets is the way that G acts on them. So if we take the image of the what we get when we act on S by G, this little g is the same as what we get when we act on phi of G, psi, I think, psi of G, psi of S by G. Okay, and you say it's isomorphic if this is a bijection. Okay, and that comes up useful later. Perhaps we're going to get somewhere soon. We're just trying to motivate get all the groundwork definitions down, then we're going to do some fun questions. Last thing that we need, I believe, is this stabilizer. Stabilizer is all the elements that say put under, or sorry, all the elements that keep S the same. So it's with respect to a particular element in your G set, it's all the group elements that keep it the same, that fix S. Okay, so yeah, some examples now before we get to the orbit stabilizer theorem. We have these ones here. So in terms of the stabilizers of orbits, first we could have what we talked about before, the group action of G on the set of cosets of H, where again we took this multiplication. The stabilizer, what we can observe, and you can check yourself, we have this property that again we'll talk about later in the slides, that the stabilizer of GH is the conjugation of H by G, in terms of the conjugation of the stabilizer of H by G, which is quite interesting, which in this case is GH in G inverse. Okay. Another example is where we have this conjugation map we talked about before. This S is an element in G. The stabilizer is what we call the centralizer of element H. It's all the elements such that they commute with this element H is a way you can think about it. And what you call the orbits are the conjugacy classes. I haven't defined them here. But what they are for an element, for an element G, it's the set, let's say HG, H inverse, such that H is in H. So G. Conjugacy class of G. Okay, so conjugacy classes and centralizers are another piece in this course that have questionable notation. Alex said he was always going to tell you what they are when they show up in the exam though. Finally, when we're talking about this normalizer that we said we cared about, when we have the group acting on the set of all subgroups, so X being the set of all subgroups of G, then if we have the action as this conjugation of the subgroup, then the stabilizer is going to be the normalizer of H. So what we looked at before, we wrote it in a different way, but now we're just bringing the G to the other side. It's the normalizer of H, which kind of just follows from how we defined it here. Okay, and yeah, I guess it's not a particularly nice way to think about the orbits, but it does kind of point out the fact that this action makes sense because we said before when you conjugate a subgroup, you also get a subgroup, so it's a nice, like, it's well-defined action, goes from one subgroup to another when you conjugate it. Okay, so yeah, this is the big theorem that we want to look at, that there's this decent morphism between the quotient group, set of cosets. So I keep saying quotient group. It's not a quotient group because it's not necessarily normal. The set of cosets of H and S when you're dealing with a transitive action, that is like, if it's not transitive, then you're saying that, in other words, G dot S is isomorphic to, G dot S is isomorphic, G under the G set morphism to G, I don't know why I have the brackets here. It's not right like this. The orbit of S is isomorphic to the set of cosets of the stabilizer in G of S. Okay, that's a way to write it when you're not necessarily dealing with the transitive action. You're kind of restricting the action to your orbit. But this is another way to write it. And what the morphism is that it takes your coset and then maps it to, since it's respect to, like the H is the stabilizer of an element S, it maps it to the action of G on S. Okay, so that's a simple way to work with it. A question like this showed up in the midterm. The corollary is that, is the orbit stabilizer, the size of the orbit times the size of the stabilizer is the size of the group orders. Okay, so we have this example here. So you may remember from the third isomorphism theorem by third iso, if H is, so if N is normal in G and N is contained in H, that implies that the corollary from Lagrange's theorem, that implies that the intersection of these two times the size of their product is product subgroup is equal to the size of H times size of N. Here, though, we don't necessarily need, we're saying that we have this result that basically says the same result holds when we don't need N to be normal, or we don't need this containment or relation in any way between H and K. So we have two subgroups, H and K, of a finite group G, so finite so we can work with the orders, and we have this action that you can verify for yourself that is a valid action. The reason why, briefly, is because if you take the identity, that what you effectively have is that this is identity, just becomes that there, and you can verify the sort of sense of associativity by looking at this and kind of intuitively saying that that makes sense. So this is a valid action, and the question kind of gives you that. You want to use the orbit stabilizer to show this result. So let's try to count, well, look at the size of the orbits and the stabilizer for this action. So I said before that when you're dealing with trying to look at the orbits, it might be good to look at a nice element to study the orbit of. So a nice element might be, let's consider what the orbit of the identity element would be. So consider, and also the stabilizer of the identity. Consider, we're going to start off with the stabilizer of this action, stabilizer H times K of the identity, which is equal to the set of H1, H2, K1, such that H1 1 inverse of this Hn, of this identity, yep, this identity is equal to the identity. That is, in other words, the set of H1, K1, such that H1 is equal to K1 if we rearrange this. In other words, it's the tuples that contain the same element, H1, H1, such that H1 is in H and K, because we need it to be in both coordinates, we need it to be in H and K. In other words, the stabilizer size of this identity element is equal to this intersection size. So that is something we wanted to look at. That's our denominator. We wanted to look at that. And if we also observe that for this is the group acting, so like H, this product is acting on, it is acting on G, we can observe that the size of this group is going to be equal to the size of H times the size of K. So we're basically done. The only thing that we need to kind of figure out then is that we have this observation that size of H, size of K over H and K, which is equal to, we kind of just showed, that's equal to the size of H times K over stabilizer H cross K of the identity, which by the morphism we just looked at is going to be, or not isomorphic, but equal to the size of H and K dot the identity element. That is the size of the orbit. So let's look at the size of the orbit. This is a different color. The size of the orbit would be H1 times K1 inverse So you write out more formally. So the size of the orbit would be everything we get out from taking everything in h times k, h1 times k1 inverse, h1 is in h, k1 is in k. But you can rewrite this in a similar way that we looked at, I think, the first question we did. This is just h1 times k. If I kind of like replace h1, k1 inverse with k, h1, just like dummy variable change to h. This is just the product of every pair of elements within h and k. In other words, the size, in other words, it's h times k. In other words, the size of it is equal to the size of hk, which is what we wanted. Wonderful. Any questions on this? Yes. Well, that's we just talked about that here. Yeah, the reason why that's true is because you're basically looking at that vector, that tuple of two elements. One of the elements is in h, the other is in k. So the size would be like that. You have kind of independent choices, number of choices for h times the number of choices for k. Any other questions? Just briefly scroll through what's written down here. Be saying the same thing. Any other questions? Okay, cool. So I believe we're up to, yeah, this little, you may remember this nice result from the board tutorials. First of all, let's just have a little bit of a formal statement of something we looked at in the example before, that if you look at the stabilizer of what happens when you act on S by G for an element S in your G set, what that turns out to be is the conjugate of the stabilizer of S by this element G, nicely enough. And that kind of leads into this nice result as a sort of corollary, but it takes a bit more work, that if you have two subgroups that are conjugate of each other within your group G, then that occurs if and only if their quotients, the set of cosets, are isomorphic as G sets. So that's to say kind of like the condition of the groups acting the same as G sets, the cosets acting the same as G sets from their stabilizers comes from conjugation. Okay, so that's a bit of a hard problem to prove if you've discussed that with Alex or Dominic, but it's a relatively nice result if you think about just the statement of it. Okay, so getting towards the questions that almost go into the seal of theorems, one that has a quite an interesting and unique proof that I quite liked in the course was the proof of Cauchy's theorem that says that if you take any finite group and a prime in the decomposition of the order of the group, then G has an element of that order. Okay, that is, there is a subgroup of order P if P is a prime. By the way, for the rest of these slides, just assume that P is a prime if I don't otherwise state it, because otherwise it's just abusive notation if I mean something different. Assume P is a prime, then you find this subgroup of order P. That's quite a nice theorem. Maybe revise the proof of that. Cayley's theorem goes back to this idea that you have this induced morphism, homomorphism from your in terms of your group action. You can think of that inducing a homomorphism to the permutation group of your G set S. And so if you consider the group acting on itself, then that's to say, since it's a transitive action, that kind of means that this homomorphism is injective. The result is Cayley's theorem that says that there is a, in your group, it's isomorphic to a subgroup of Sn because it has trivial kernel by the first isomorphism theorem. Okay, so last big result before we get to the seal of theorems is Burnside's lemma, quite interesting. So this is a nice one to use in certain cases of proving results. I guess last theorem before we, besides the class equation. We'll get to that as well. Just remember this notation is just a more general way of, well, more general than what we have in Birdside's lemma, which just focuses on the fixed points of acting by one element G. It's saying that if you take a subset of your group, you say that the fixed points of that subset are all the elements in the G set that say fixed, as in don't move anywhere, when they're acted upon by all these elements in H. And Birdside's lemma says that the number of orbits, remember we said this was the number of orbits, this was the set of orbits, is going to be the weighted average of the fixed points under each of the elements in G. So we'll just use that briefly in this question here. Hope you remember it from the board tutorials, showed up in one of the final exams. If we have a group that's acting transitively on a finite set with more than one element, so that's to say this S is greater than or equal to 2, show that there's an element G without fixed points. So the way that we're going to work with this briefly, hope you remember some sort of similar approach you may have had in the tutorials, is if we write G as the sum, rearranging Birdside's lemma, G and G of the fixed points, we can say, split this up into the fixed points of the identity plus the fixed points of everything other than the identity. S power of G. The fixed points of the identity fixes everything, so that'll be S. And then if we assume, for the sake of contradiction, that this second term, if we assume that every single element G has some sort of fixed point, then this would contribute 1 to each of those fixed point sets. So basically what we want to argue is this would be G minus 1 if there are no elements without fixed points. But that is, since S is greater than or equal to 2, that's strictly greater than G. And so that's a contradiction. You get that the size of G is strictly greater than the size of G, which is nonsense, of course. Okay, so that's what we basically argue over here. All right, so let's move on. Get the result. So recall what we defined before, which is the center. We have this result of the class equation. The class equation is just a way to write what we said in regards to the set of orbits forming a partition of your G set. I might have said before they form partition of the same size. That's not true. The orbits can be of different sizes. In this case, the center is relevant to us because it comes up in the conjugation action. So G acting on G, where G dot, let's say G dash is equal to G dash G inverse. What we said before, the centralizer of G, should say stabilizer in G of xi just being an element in X, is what we call the centralizer of G of xi, which is the set of elements where this action leaves this xi fixed, that is, set of elements G and G, such that G dot xi is equal to xi, which we can rewrite in terms of the stabilizer. Oh, the stabilizer we can rewrite it in terms of what we defined before for the centralizer is G in G, such that G xi G inverse is equal to xi. Okay, that's the centralizer of G. And so what this is saying, this index is the size of the conjugacy class, because we said before, orbit stabilizer theorem, size of the conjugacy class, G xi is the size of G over size of stab G. psi, which is equal to the size of the quantity class G dot X, which is what we want. Quantity class. Okay, that's what this side of the sum is saying, but all we're doing here to make it a bit more nice to write out, especially when we use this in P groups, is that we separate the center because we're looking at xi as representatives of the conjugacy classes with more than one element if the element is in a conjugacy class with just itself. That means it commutes with every single other element in the group, which means it's in the center of the group. That is to say as well that the centralizer of that element is going to be the entire group G, so that contributes 1 to the sum. So you get an addition of 1. If you look at the sum of the sizes of all the orbits, you get in total the center plus the sum of the non-trivial indices of the centralizers. So yeah, we have a question right after this. The follow-up from that is that if we have a prime P, what we call P group is a group of order P to the n. So a prime power. A nice corollary of the class equation is that if you remember Lagrange's theorem in regards to this index and you take modulo P on both sides of the equation, you can deduce that this center, which contains at least one element, that being the identity, is going to be non-trivial because it has to be divisible by P in size. So the center is non-trivial, and there is this also result we proved in class, as is also a bit non-trivial, that there exists a normal subgroup of order P to the m, where m is some number between 1 and n. So that's a nice result. Let's look at this example here. So I won't go to the full details in the interest of time, just walk through the brief details. We're looking at a group of order P to the 3. We want to prove that the quotient group, I can finally say quotient group again, is isomorphic to this direct product of z modulo pz with itself. So there's kind of two steps we would follow for this that would lay out. Since we're dealing with a P group, what we might think about using is this class equation. Well, the result that we have is that the center is non-trivial. So we know, I'm just going to draw arrows because I'm getting a bit lazy. We know that the center of G, the size cannot be 1. It has to be, can't be non-trivial. It has to be P, and by Lagrange's theorem, P squared, or P to the 3. And since we know this group is non-abelian, let's look at the 3 different cases that it arises. One, if the center of G is equal to the size is P, then we look at G over center of G. Okay. And what we have to realize, come back to that, this quotient group, this quotient group has size P squared. And so this is admittedly a bit of a difficult question to do on the spot. I don't expect you to be able to do this immediately, but the quotient group has size P squared, and so is abelian. So you may remember from, say, the midterm or otherwise, there was a tutorial question that got you to prove that every group of order P squared is abelian. And so is abelian. And so it is either isomorphic to z over pz squared or z over p squared z. And we'll just put a little pin in this for now. If it is isomorphic to this, then we're done because that's basically what we wanted to show over here. But we'll come back to that. There is a more general result that will let us handle this and some other cases later. If the center, in the interest of time, is of size p squared, then z g over G over ZG has to be isomorphic to Z over, actually, what am I doing here? Actually, yeah, we can actually ignore these. No, we can't ignore these, sorry. We'll just state it like that for now. And 3 is if ZG is P3, then Z over, sorry, G over center of G is isomorphic to just the trivial group, which is abelian. Or in other words, which means G is abelian. Sorry, because we want to contradict the fact that we know that G is non-abelian, which means that G is abelian. Okay, forgive me. And then for these last two, I'm going to use a result that I'm going to state without proving. The result is that if G over ZG is cyclic, Justin's favorite result, I keep saying that, then G is abelian. So we can cross out these two results, these two possibilities. The only one that we're left with is the quotient of the center is isomorphic to, oh, I wouldn't say isomorphic. I'm just going to rewrite it in my favorite way, Z mod PZ squared. I'm just rewriting it in a different way, the way I prefer to write it. Okay. Any questions on this? Otherwise, we'll move on in just the time. Cool. Right. So Sylow theorems, we'll look at these and then look at 2 to 3 questions on them. So you should be familiar with these by now. Maybe you've forgotten them since the midterm. So there's 3 theorems, and then there's like what I might call the Alex lemma, and there's 2 other nice results that you can look at. The first theorem says that if you have a group G that has, so G is equal to P to the N times M GCD, and assume this for the later parts, P to the N, M is equal to 1, then what we say is that a group of size P to the N is a Sylow P subgroup. Sylow's first theorem tells you that one such subgroup exists at the very least. The second one tells you, it doesn't just tell you like the obvious fact that if you conjugate a Sylow P group, then it's also a Sylow P group. You get that immediately from the fact that conjugating a subgroup is also a subgroup. But what rather it tells you is that every P-love subgroup is obtained this way. So in this kind of group action sense where you look at the conjugation of a subgroup, every Sylow subgroup is a conjugate of another one. You can produce them all by conjugation of one of them. It's interesting. We'll look at an example of that. The last one is in terms of the number of Sylow subgroups. It's another interesting result. It divides this M that we have in kind of the residue when we suck out the P factor from G. And it's also modulo 1, it's 1. So modulo P, it's 1. Okay, that's the third one. So of these next ones, they might come up in handy when you're dealing with problems. The second one is saying that if you conjugate a P subgroup that has size P to the M, where P to the M is less than or equal to N, then there is, if you conjugate it in some way, there is a way to conjugate it such that it lies within one of the Sylow P groups, is what it says. And then the final 2 lemmas, this one follows from the result we saw before, that there is a subgroup of size P to the K for any K between 1 and N. And then finally, Alex's lemma, as I like to call it, that comes up quite in handy, that was used as a lemma to prove the Sylow theorems. The size of the fixed points of S is congruent to S mod P if the fixed points is respect to a P group. That's another important result. So we'll look at these examples now. This first example is we're dealing with trying to construct a index of size n to the np. So remember, np is the number of Sylow subgroups, p is a prime. We want to show that there exists a subgroup n such that the index is equal to np. So what we want to do, we want to think about how we can get np to show up. So with questions like these, you always want to think about what type of group action can I try to induce to get this np or whatever it is I want to show up. So for this case, what I might think to do is, well, I said before, all Sylow P subgroups are conjugates of another. That is, they can be produced by conjugation of one specific Sylow P group. So I might consider that as, say, the orbit of some sort of group action. So the size of the orbit would be NP, and then I could deal with the maybe stabilizer being my group H that I want to look at. So that motivates what I have chosen, which is consider, and this is always kind of like the, you know you're going in the right place when you consider the right group action. Consider the action of, I think it's G. Consider the action of G on G over P, no, forgive me, X, where X is the set of subgroups of G, and let P be a Sylow subgroup. Then, what I claim from second ISO, the size of P, size of G dot P is going to be NP. And we stated before that the stabilizer of P under G, that's going to be the normalizer of G in G of P. So what we have by orbit stabilizer, we have that the size of G dot P is equal to the size of G over the size of the normalizer P. That is the index of the normalizer in G. Okay, any questions on this? And that's what we wanted. That's the NP that we wanted. So you can see more details in the slides. That's the basic idea of what we do. Any questions? Right. So that's what we want, NP. Yep, so written out like this, sure. Okay, next example. So second last example for this section. We're looking at a subgroup H over Sylow. Sorry, subgroup H, and forgive me, the normalizer of a Sylow P group, P, is contained as a subgroup of H. We want to show, and specifically, instead of saying that P is a Sylow P group of G, it's a Sylow P group of H, so not necessarily of G immediately. We want to prove, in fact, it actually is a Sylow P group of G. So we want some sort of way to work with the normalizer. We saw last time we could say the normalizer is the stabilizer when we look at the group action on the set of all subgroups. So we could try that again, see if we could get that normalizer to show up in a nice way. But I'll show you another way that the normalizer typically shows up, is that we looked at before Alex's lemma that told us that if P is a P group, then size of S is congruent to size of the fixed points under P, mod P, little p. One's big P, one's little p. Don't get confused by it. I guess there's not really a better way to write it. And one common result that happens when we consider the group action, which makes somewhat sense here, maybe it's the only thing we could try to do where we act from P act from G acting on G mod P. I have that right. Then the set of we have G over P is congruent to the set of fixed points of G over P, P mod P. And an exercise you can show that this is congruent to, or in other words, the set of fixed points of the set of cosets under P is congruent or is the same as the normalizer of P, quotient P. Okay, that's an exercise you can show. You can prove it directly by, this is when you're dealing with by multiplication. So regular group multiplication, this is a result that shows up and can be used in a lot of different contexts. You hopefully have seen a few of them already. This is a different one. So what happens is that this is congruent to ng of P over P mod P. And the basic idea, I won't go into the full details, the basic idea is that if big P is not a Sylow subgroup of G, so we're looking at a sort of contradiction approach to this problem. If this P is not a Sylow subgroup of G, then there is a factor of P little p in G that's not within the size of the Sylow subgroup. So this would be congruent to 0. This size, the number of cosets here would be congruent to 0 by Lagrange's theorem. And so this would also be congruent to 0. That's if P was not a Sylow P group of G. But we know the normalizer of P is contained within H. And so what that means is that as a subgroup, you can apply Lagrange's theorem again for Jimmy. As a subgroup, we can apply Lagrange's theorem again. What that tells us is that let's say, yeah, the size of H over the size of P is congruent to 0 mod P. If P is not a Sylow P group. Okay. Which is a contradiction because that says that there's some residue left over in H that has a power of P in it, but that contradicts the fact of P being a Sylow P group of H is the essential idea. Any questions or problems on this? In the interest of time, I'll move on to the next one. Okay, last question on group actions then. Let's have a look. Is this one here. So this is from the sample midterm. We're presenting a different way to do it, suggested by a lovely Jeff in the audience. That is different to the way you may have done it yourself. That can use pretty much the same Alex lemma that we just looked at. Instead, we're going to do a bit of a more direct argument. So we will consider the group action. And this kind of shows the idea that just play around with group actions and see what happens when you're kind of stuck trying to find what action works. Consider the group action of P acting on G modulo P. Well, it's not. Yeah, G modulo P, the set of cosets of G and P, P and G. And what we need to consider is that the size of G modulo P is the sum of the size of the orbits. Like this maybe. And this has size P because the size of G is P to the n size of, by assumption, size of P is size P to the n minus 1. So this has size P. And so what we need, since I guess each orbit has each orbit as well. So the orbit is equal to the size, and this we're going to get a bit loose, this is equal to the size of P over the size of the stabilizer. That's to say, since P is a P group, the size of the orbit is either equal to either 1 or a power of P. Okay? So basically the essence of this argument would be to say, since we're summing these positive numbers, there's two cases we have to consider. That is, two cases emerge, which is the first one saying that one orbit has size P, that is, the action is transitive, but this can't occur since the orbit, if we look at, say, the identity element, which is like your go-to example when you're trying to contrive a contradiction, orbit of the identity element G dot E, I'm sorry, forgive me, P dot E is just P, which is going to be 1, because it just gives you the one coset being P itself. You only get one coset out. And so 2, we have to have each element in P is in its own orbit. So what that means, each element is in its own orbit. The implication of that is that for all, let's say G in P and G dash in G, since it's in its own orbit, it can only have that G dot, actually I'm going to say G dash P in G over P. G dash P has to be equal to G dash P, but that means that G dash G dash, and this is inverse, P is equal to P. In other words, we're going this long argument to show that the conjugation of any element in P under any other element in G lands you back into P. And that's to say, we'll write it down here. Well, we wanted to show, if you remember again, we wanted to show that P is normal in G. And so that's the result that we have here. Okay. So my exercise that I have for you all is now to verify all those details I skipped in the proofs. And as I said, look at the lecture slides and the lecture notes to get the precise details for all the rest of the content I skipped over briefly because of the interest of time. And look at that, Alex bought lunch for me. Wonderful. So questions over the break, you can have a look at them here. Justin prepared these for you, so we can talk about those over pizza. After the break, we'll be looking at ring theory, so we'll be having a break. For those of you watching online, the break will be us eating pizza, so unfortunate for you not being in person. Sorry for you. After the break, we'll be looking at ring theory. Jeff will be presenting for us, followed by Daniel presenting the last one. So if you have any questions, ask me in the break. We'll start the break now, and you can have a look at these break questions. Excellent timing, Alex. Make sure you've scanned the QR code already. If you haven't scanned the QR code, please do so. What's that, sorry? Yeah, I got margarita inside. Oh, we should do the photos now, I guess. You just take a photo. You can do that now. If you want to do it now. Yeah, I'll hold mine for a minute. Do you want the photo now? Yeah. We can get like a pizza in it. Yeah, do like this. I don't want to be in photos. Okay, sure. We'll upload the slides after the seminar's finished. They should be on MathSoc. We'll make an announcement with Carly. I remember the second one was like had a lead solution.
5 right now. Well, this is 3 hour test. No, I heard a lot of additions, right? Oh, just some German. Yeah, yeah. No, like a lot of open slots. That's what I heard. Oh, yeah, like this. Yeah, so we need to be on study CS. Like an integer is CS for the single one. What is it? This one? Just talking. Really want to calculate is pretty challenging. Do you want to visualize the 9 hour? That's the better question. Back and forth. So one, 9 hours. 5. Use 5. If that was 9 hours, that would not be. That would be. Have like. That would be have like jealous. Might be 9 hours. Oh, okay. No, I heard about that actually. If you have TLS. No, like ELS. Like the. Oh, wow. Dude, some people get an extra 30 just per hour of their exam. Yeah. So just imagine like 5 hours plus. So. I know that one goes down 30 to leave. Like I'm not held like requirements saying that you can't take a 9 hour exam straight. Like 1 second. Oh, well, I mean, you can go out whenever you want. You can take a break whenever you want. Yeah, yeah. Or you can do what I did and fall asleep halfway through. What? Don't worry about that. It's that hard. Yeah. You was just like me talking about most people they spend the whole 5 hours living in so few questions. Yeah. Last year was especially good one. The average was 150 hours. I always from budget. Oh, it's 150. You took it last one? Yeah, I took it last one. Oh, yeah. I think it was around 150. Around 150, yeah. There was this one guy. So there's only 7 problems, right? There was this one guy. Only one guy who solved 5 problems, and second place was like 400. It's like 4 problems, and then everybody else is like, you have something, you have something. It's like the street money. The code did probably for that to minimum one thing. We're gonna be going through all the 3 or 4 balls, but I don't like the dominant code for that code, so I am. Yeah. Is that fine? Oh. You can hear me now, right? All right. Yeah, so it's ring theory time. Finally done with group theory. Yeah. Oh, this full screen? Oh, yeah. Igor. Yeah, guys, sign the attendance form. Not that you have one. Okay. Yeah, so it's rings time. Finally time to talk about rings. How interesting. So what is a ring? Is this a ring? Unfortunately, we're not doing a ring making class. We're doing abstract algebra. So a ring is a set with these 2 operations, which we call addition and multiplication. And then much like a group, well, actually, it is an abelian group under addition. But for multiplication, it shares similar properties with like groups. So for one, there is a multiplicative associativity. So the multiplication operation is associative. And then there's also a multiplicative identity. So if I multiply anything in the ring by it, then it just remains the same. But interestingly enough, we don't allow for multiplicative inverses, or like we don't need them per se. But more on that later. And then the final condition is distributivity, which is basically tying together how addition and multiplication relate to each other. So it's kind of like, when you're working with the integers, you can expand out the bracket into, that. And obviously there's 2 directions as well, because we don't necessarily have to assume that the multiplication operation is commutative. And then I put the asterisk there. Oh yeah, sorry. Yeah, a commutative ring is just when the multiplication is commutative. because it's already abelian under addition. And then I put a little asterisk over here because we assume 1 is not equal to 0 in a ring. Otherwise, you get some like weird like stuff happening. And you get the trivial ring, which is just 0. Which, I mean, it works, but it's like, you know, it's a bit weird. And so we prefer to have like a distinct multiplicative and additive identity. Yes, so if you've done or are currently doing Math3431, you might be saying, wait, the definitions I saw in that course for a ring is different to this course. And for those of you who don't know, an Alex ring is an eagle ring with an identity. I.e., the one you learned in 3431 doesn't have a multiplicative identity. But why is that? Why do we have it in this course? Basically, if we know it exists, it's quite helpful to prove a lot of things. So when I talk about ideals later, it will become quite apparent. But for now, just accept it. We have to have a multiplicative identity. But also, it's kind of like hard to think of a ring without one besides like the trivial ring. So yeah, it's generally easier just to have one anyway. So here's some properties of rings. If we have a ring with elements Rs, then anything times 0 is just 0. And then -1 times R is the additive inverse of R. And then we have a similar thing here. It's kind of like a negative times negative equals positive type situation. And these are quite easy to prove. In fact, we've done some of these in the tutorials. And then now we have a subring. So it's just a subset that's a ring. And then since the operations are inherited, all we need to check if it's a subring of like some bigger ring is if the multiplicative identity is inside. There's this condition, so it's basically closure under addition and additive inverses simultaneously. And then there's this, which is basically just closure under multiplication. And then everything else would be inherited. So these are the only 3 like conditions you need to check. Yeah, and then also in a section of subrings, also subring, and should be pretty easy to show, hopefully. Yeah, this first half of rings is mainly definitions, so I'll be reading out a lot of definitions, so it might be quite boring. Yeah, and speaking of another definition, a unit is just an element with a multiplicative inverse. And then we can denote the group of units as R times, which is basically what Brendan was saying earlier. And yeah, this forms a group, also pretty easy to show. And it shows up sometimes as well. Yeah, and then if all the non-zero elements are invertible, i.e. R times is equal to R minus 0, then it's called a division ring. And if it's also commutative, then it's a field. And we'll talk about fields a lot later on. Daniel will be talking about that. Yep. So similar to group homomorphisms, we have ring homomorphisms. And of course, it's between 2 like random rings. And then it preserves the structure of addition. But now, since we have the extra operation, we also have to preserve the structure of multiplication. And then we also want to map identities to each other, which is also another reason why we need identities to be existing. And then, of course, if it's bijective, then it's an isomorphism. And we also have these properties. So if we have the image here, which is just like all the possible outputs, and then the kernel, which is all the elements that map to 0, then the image is a subring of the like codomain, and then the kernel is a subring of the domain. And then the kernel is also, well, these are both also like ideals, but I'll talk about that in a sec as well. Let me pause the camera's disconnected. Just the OBS camera's frozen. Yeah, it's still showing me. I'm Brendan, guys. Yeah, Luke my butt. Completely about rings until we return. Yeah, question for you guys. Find a ring with no 1. Oh, is it back? 2Z. Find a ring without a multiplicative identity. You can think about that in the meantime. Yeah. And then finally ideals. So ideals are basically like the analog of like normal subgroups in like rings, because obviously subrings behave a bit differently. So what we say an ideal is an additive subgroup such that of R, such that when you multiply by anything in R, it remains inside the ideal. So basically, I don't know if I've written it here. Oh, basically like R times I is equal to I times R, which is equal to I. Yeah. So basically, this kind of looks like the condition for normality in when we do group theory. So this is kind of like the analog to that. And then, of course, we say it's simple. A ring is simple if the only ideals are the one generated by 0 and the ring itself. And then we can also generate ideals by just taking linear combinations of every single like linear combination of elements inside like the generating set. So it's basically the way to like get every single possible element, so you can write it out as a set. And then here's some properties. So let's just say I is an ideal of S, and then we have this ring homomorphism R to S. Then we have the ideal is equal to S if and only if 1 is inside the ideal. Obviously, you know, if I multiply 1 by anything, I just get like, say, R. So 1 times R equals R, and then R is just anything in the ring. So that's how you can see that if 1 is inside, then it must be the whole ring. And that's also one reason why we include multiplicative identity, because we just get that condition for free, basically. And the second one is, yeah, the pre-image of an ideal is an ideal of the domain ring. And then the kernel, which is the pre-image of 0, is also an ideal. Yeah, and then the intersection of ideals is also an ideal. So here's a little example. This was in one of the problem sets. Yep. So prove that every simple commutative ring is a field. Well, what does it mean for it to be simple? That means the only ideals are just R and 0. Yep. So the solution is you just consider the ideal generated by any non-zero element, and it must be equal to R. But if it's equal to R, we use the previous fact that 1 must be inside of it. So that means there exists some element R dash, where if I multiply it by R, then it becomes 1. And obviously, since it's commutative, the order doesn't matter. So the left inverse and right inverse are the same here. And that is what R prime is. It's the multiplicative inverse of R. And this works for every single non-zero element. So while we're in a commutative ring where every non-zero element is invertible, that just means we're a field. And then we're done. And then, yeah, similar to quotient groups, we can kind of mod out by an ideal. And then we just write it as like R plus I for like some thing in like R mod I. It's kind of like a coset in a sense, and it behaves quite similarly. So if we have like two of these like cosets, if you will, multiplied, then you just multiply the representatives and then add on the I. Why does it say this? I don't know why it says that. Yeah. And then this is the multiplicative identity, 1 plus I. And it's quite easy to see. If you don't have 1, then it's a bit tricky. Okay, now it's just the ring isomorphism theorems. So similar to the first isomorphism theorem for for groups, we have that if we have a ring homomorphism R to S, then R mod the kernel is isomorphic to the image of the homomorphism. And in this case, the actual induced isomorphism is quite similar here. It's like a phi bar of a coset is equal to just take the phi of the representative. Yeah, so that's first ISO. And the second ISO is if we have a subring of a bigger ring R, and then we also have an ideal of R, then S plus I is a subring of R, and then the intersection of the subring and the ideal is ideal of S. And then we have this sort of like fraction property thing here. So S over S intersection I is isomorphic to S plus I over I. Yeah. And then third iso theorem, very similar to the third iso for groups again. It's basically like the cancellation of these quotient rings here. So as long as J is contained inside I is also ideal, then we can kind of just cancel off the fraction part of the J, in a sense. And then fourth iso theorem, basically the structure of the ring and its ideals, and which contain a certain ideal, is the same as its image under the quotient map, basically. So what does that mean, exactly? Well, let's just say R is like the ring, and then let's just say, well, in this case, J would be like the ideal that's contained inside every other ideal. So there'd be a string of ideals here down to J. And then these are all ideals of R, and J is contained inside all these ideals. What the fourth isomorphism theorem tells us is that when we take the quotient map here, say pi, well, this is actually a bijection here, this mapping. So it could be a double arrow here. So it'd be I1 mod J, and so on. J mod J. And then these have the same structures. So for example, I1 mod J is contained inside R mod J, and so on, basically. And then these are ideals of that as well. I feel like this is the most important one, but it's also the most abstract one out of all of them. Okay, now Chinese remainder theorem. So this is the ring version of it. If you've done any other courses, you might not have seen this, but this is the very general version of it. So if we have a ring with these set of ideals I1 to In, and then these are well, the condition is called pairwise co-maximal. But what that basically means is if I add any two of them up, then I just get the whole ring, as long as they're distinct. And then I choose this big I to be the intersection of all of these little 1 to n ideals. And what the Chinese remainder theorem tells us is that this homomorphism here is an isomorphism, actually. So R mod I is isomorphic to R mod I1 times all the way to R mod In. But I think if you've done any sort of number theory course before, or just have dabbled in number theory, then this version is a lot more common, which is basically saying if I have these pairwise coprime positive integers, so n1 to nk, then I know the solution. There's a unique solution to some congruence equation modulo n, where n is the product of all these integers. And this just follows from, I guess, the main ring version, because you just consider these ideals n1z and whatever z, and then yeah, you get the same result. So for the remainder of this course, our main focus is on polynomial rings, because that's just what we're working with, I guess. I don't really like this definition. You might think it's very weird, oh, I thought a polynomial was just ax plus b squared plus c or whatever. In a sense, this definition is capturing that, but it's a bit more abstract. So this is the definition in the lecture slides, and then the way Alex has done it is basically, well, Pn is just the coefficient of the x to the n term. So that's why you say all but finitely many n, because a polynomial has finite degree. So eventually some p, I like to say pk, just becomes 0 for any k greater than k. And then obviously if you add up two polynomials, you just add up them coefficient by coefficient. And then what happens here is this is basically convolution. So when you multiply two polynomials, the nth coefficient will just be this convolution sum here. But honestly, we don't really have to think about it in terms of this. This is just an abstract way of defining it. We can just think of it as our normal, ax squared plus bx plus c and so on. You can also think of it as a sequence of the coefficients, which is pretty much what this is doing as well. Yeah. And then we just call this to be Rx, where the coefficients are in R. And then, of course, it's quite easy to extend it to multiple dimensions, considering you can just play around with the operations. You can kind of like adjoin each x each time, kind of. So here's an example. This is from, I believe, Artin's algebra. So we can think about the automorphisms on the polynomials over the integers and what they are. Anyone have a guess? Who would like to guess? All right. Okay, well, I'll just show you how to do it. Okay, so let's just say phi is some like automorphism inside this group, or like this set, and then let's just restrict the domain to the integers. When we do that, because we know that ring homomorphisms maps identities to identities, we must realize that phi must fix the integers, so it's like the identity homomorphism in this case. So let's just consider what happens when we apply phi to like x, which is the generator for every single non-constant polynomial, or like without a constant term. And let's just say it's just some polynomial x, p of x, like it maps to that. So, well, we know that phi is an automorphism, so it must be invertible, right? But let's think about the only polynomials that are like invertible inside Zx. But in this case, it would actually just be, well, degree 1 or like linear polynomials, because if you wanted to say invert like x to the n, you'd need a x to the 1 over n term, which is like not a polynomial. And obviously, if you be a bit more rigorous, then you can do this calculation here. So both of these degrees must be 1. And then, of course, invertible linear ones inside Zx would just be plus or minus 1 for the leading coefficient, because again, you can't have fractions. So we can just write p of x is equal to ax plus b, where a is either plus or minus 1, and then b is just some integer. And these form all the possible like automorphisms. Yeah, so it'd be this form. And the thing about this is like if you're like keen-eyed, you can also notice it's isomorphic to d infinity, or like the dihedral group of infinite order. If you can see why, then like it's pretty good. But we didn't really cover that group that much, and that was part of the question, but I didn't really want to include it because we didn't focus on that too much. Anyways, so now we just want to move on to ring adjunction. So if I have a ring R, I can add on these elements A1 to AN such that this is actually a ring. So when I write R, A1, A2, AN with the square brackets, that means it's the smallest ring generated by R and those elements. And don't get confused with the curved brackets. That's a very fatal error. Do not do that. But I'll talk about that later, hopefully. Not a definition. Yeah, sorry for bombing you guys with definitions, but that's the first half. We say an ideal is maximal if the only ideals containing it are R or N itself. So you can't really have any ideals with the same elements that are larger, basically. That isn't like the ring. And then we have some properties of maximal ideals. So R mod n is simple. This follows from 4-FISO theorem. And then M is maximal if and only if R mod M is a field. I want to walk through like the converse to that, because I think it brings some nice insights into like how to think about rings and ideals and stuff. So we claim that if R mod M is a field, then M is maximal. Well, let's think about it like this. Okay, if R mod M is a field, it must be simple. Why? Because let's just say I have some element. Well, I can just multiply it by like A inverse in the ideal, and then you just get 1. So if I had some ideal of like this, R mod M, I can always just make it have 1 inside of it, and then that means it has to be R mod M. Unless, of course, it's 0, but then either way, you just prove that's simple. So since it's a field, we know it's simple now. And then by fourth isomorphism theorem, the only ideals of R containing M are R and M. So that must mean M is maximal by definition. Okay. Another definition. So integral domains. It's just a commutative ring with no zero divisors. And when I say zero divisors, I mean two non-zero elements that multiply to give you zero. So for example, in like Z mod 4Z, 2 times 2 equals 4, which is 0. So that in that case, that wouldn't be a integral domain because you have these two non-zero elements which multiply to give you 0. I think we should note that like every like polynomial ring is also a integral domain. Yeah, and here's some properties. So the main one is just cancellation. So if you have like RS is equal to R prime S, sorry, RS prime, where R is like non-zero, then you can just cancel off the R, even though you don't need multiplicative inverses. So even if R is not invertible, you can still cancel it off, which is quite useful. And then R is isomorphic to a subring of a field. I'll get into that later. So here's an example on integral domains. So prove that every finite integral domain is a field. So this was from like the problem set or something, I don't remember. Let's do a quick walkthrough in the interest of time. So we just consider a map, phi r, where if I plug in a, then it just multiplies by r on the right or left. It doesn't really matter since it's commutative. Well, it suffices to show that since, well, R is finite, if the map phi is injective, then that means it's bijective because it's the same cardinality. So using the definition of injectivity, phi r of a is equal to phi r a dash. That implies that AR is equal to A prime R, but by cancellation, A is equal to A prime, which means it's injective by definition. So it must be a bijection, and then basically, I'm going to have to get to 1 somehow, right? Because every single element is mapped to, because it's bijective. So there exists some element A, such that when I multiply it by R, it's equal to 1, which means that R is invertible, and also A is invertible. And this works for any single like non-zero R. So that means every single non-zero R is invertible, and then we're done. It's a field. Okay. So this is what I was talking about before when I said every integral domain is isomorphic to a subring of a field. We kind of like force it to like work. So we just define the fraction field in a sense. So what I mean by fraction field is like the set of well, these sort of like fractions, but I just make it like a two-tuple basically, A, B. You can think of it as like A over B, but like obviously division's not always like well defined. So so I define this set R hat, which is the set of these two tuples where the B is never equal to 0. And then you can also define this equivalence relation, which basically tells you when two fractions are equal. And this is basically like when you multiply or like cross multiply like two fractions, and then you check that, you know, they're basically the same thing. So from that, we can define K of R, which is the set of all the equivalence classes under that relation tilde. And then we define square bracket AB for the equivalence class containing AB. So for example, like all the fractions that simplify to 1 over 3, that's one equivalence class in like the integers, or like all the fractions that simplify to like, I don't know, 6 over 7. And then, yeah, we can just define these operations, addition and multiplication, as like kind of normal, like kind of like how we deal with the rational numbers. So we have this and that. I'm not going to read that out. And it's also well defined because no matter which representative you choose, it's always going to give you the same answer. And that's also kind of easy to verify. And then, yeah, this is also a field because, well, if I have this element, I can just multiply by BA here, as long as A is not equal to 0. And then that will just give me 1. Yep. Another definition, favorite. So we say an ideals principle if we can just generate it with one element. So it's kind of like a cyclic like subgroup in a sense. And then we say an integral domain is a principal ideal domain if every single ideal is generated by one element. So some examples include like integers, or I think even Gaussian integers, yeah. and like polynomials over one variable. Oh yeah, I've written them out. Perfect. Oh yeah, this one, not a principal ideal domain. Why? Because this ideal cannot be written as like generated by one element. So don't get confused here. There's no division algorithm here. You can't really do any like funny magic to make this ideal to like um, be expressed as generated by one element. Yeah. And then now prime ideals. So we say an ideal is prime if one of the following holds. So A, B, and P implies either A's and B, A's and P or B's and P, or equivalently, R mod P is an integral domain. So I've just included this question here so we can kind of see partly like why these two are equivalent. So we just need to prove that in a finite commutative ring, every single prime ideal is maximal. Of course, if it's a finite integral domain, then it's going to be like a field, and then that implies prime ideal is maximal. But I want to go through it like kind of the long way. Let's just say you didn't know the second condition here. So let's just say R is that like finite commutative ring with prime ideal P. Then it's just all we need to check is basically that it's a finite integral domain, because a finite integral domain is a field. And then if it's a field, then that means if R mod P is a field, that means P is maximal from before. So let's just say that A plus P and B plus P are zero divisors. Then that basically means that AB is inside P. But since it's a prime ideal, either A is in P or B is in P, which basically means that one of these has to be like the zero in this sense, which means it's an integral domain by definition. And then that means R mod P is a finite integral domain, and then we're done basically, because finite integral domains are field, blah, blah, blah. And then that's kind of how you show like this second condition here from just the first one. Okay, I'll just quickly go through some of the like start of factorization theory before I like hand it over to Daniel. So it's mainly just definitions. We say R divides S if S is equal to RT, similar to like integers, I guess, like 1 is a multiple of the divisor. And then if they differ by a factor of a unit, then we call them associates. And then here's some properties. So in an integral domain R, if R divides S, R divides S if and only if the ideal generated by S is a subset of the ideal generated by R. And then those ideals are actually equal if and only if R and S are associates. And then it's kind of hopefully simple to see partly why these hold. Yeah. So here's a little example putting like everything together so far. So this was like very early in the tutorials for some reason, even though it's like a lot easier to do if you have like all these techniques so far. So that's why I've kind of put it here, because I think a lot of people skipped it. So now you get to finally do it using all the texts you've learned so far. So I guess by full isomorphism theorem, the ideals of Cx mod x to the n correspond directly to the ideals of Cx, which contain ideal generated by x to the n. So let's just, and Cx is a PID in this case, so every ideal will just be like generated by some polynomial. And let's just say that this ideal x to the n is contained inside that ideal. Well, by the previous little property, we know that P of x must divide x to the n. And its divisors must be 1x, x squared, all the way x to the n. So that means P is one of those. And then by the full iso theorem, we can just take the image under the quotient map, and then we get these are the ideals of Cx mod x to the n. Yeah, so we had to use full iso, we had to just use the divisor thing, had to use some like quotient stuff. It's like, yeah, I don't know how he expected us to do this in like week 7. I think these are the final few definitions. Yeah. So, okay, we see an element is irreducible if the only things that divide into it are units and associates of it. And then we say it's prime if P divides RS implies P divides R or P divides S, which is basically the same prime definition you might have seen in like number theory, but only now it's more general and applied to rings. And then P is irreducible if and only if the principal ideals containing P, ideal generated by P are that and the ring itself. And then P is prime if and only if the ideal generated by P is a prime ideal. So that's a nice little like proposition. I guess the final little fact, little lemma, every prime element is irreducible, but we should note that the converse is not always true. It only holds in, I believe, UFDs, which is the next topic, and Daniel's turn. Oh wait, he was not the one with me. Sure, it's just take the switch. Sure. Wait, did you put this in your pocket? I'm talking about the. What about the mic pack? Like, what about this?
Just clip it onto your pocket, however you want to do it.
Right, sure.
Is it on?
Yeah, yeah. Is it? It's on.
Doesn't sound right. Yeah, press this button.
Right. Okay, nice. So yeah, we're going to get onto UFDs. Yeah, so UFDs, I'll basically say that the intuition for them is that like essentially is the fundamental theorem of arithmetic, right? Because in positive integers, we have a result that you can have any integers uniquely the product of prime numbers. So we sort of want something similar. You can already see an issue with trying to do that for like Z, because like you have negative numbers. But we'll make this pretty precise. And we also know this isn't true in all rings. We've written an example there where it says 6 factors into 3 times 2, or 1 plus square root of -5. And each of these elements are prime, prime in a suitable definition sense. So we'll get more specific with what we actually mean by this. So again, just a recap, because Jeff already talked about these. In this case, we define prime. Let's see if this works. Yeah, in this case, we define prime by the property that if P divides R times S, it implies that P either divides R or P divides S, right? We make a distinction that this is different to irreducible. So we say that a non-zero element and a non-unit element is irreducible if every factor of R is either a unit or an associate of R. So essentially, if I can write R, let's see. I can write R as A times B, then either A or B has to be a unit, or a unit, and then the other is an associate, right? These are some pretty important properties. I won't prove any of them, but I'm pretty sure you guys are familiar with them in the sense that they get used a lot in proofs, especially I think the fourth one also gets used a lot. The fact that if an element P is prime, then we have it's if and only if the ideal generated by it is a prime ideal. So yeah, in a commutative domain, every prime element is irreducible, but the converse is not true, right? So every prime element is clearly irreducible because you can literally just take the prime dividing itself. But irreducible elements are not necessarily prime. I guess an example of that was like something we saw before. 6 is equal to 2 times. Whoa. 6 is equal to 2 times 3, which is equal to 1 plus square root of -5 times 1 minus square root of -5. In this case, we have 3 is irreducible. Clearly not prime, because 3 doesn't divide any of these two. Does that make sense? Yep.
So yeah, the definition of a unique factorization domain is that essentially, I'll just quickly skip it. It's saying like what an element can be decomposed into like a product of irreducibles, and this product of irreducibles is in a certain sense unique, but unique up to associates, right? We need this unique up to associates because we want to put it for Z, as we said. So maybe I'll just like talk about this quickly. Yeah, we see that over Z, 10 is equal to 5 times 2, and I said like, oh, there's an issue because you can do negatives, right? Negative 5 times negative 2, so it's not unique. But negative 5 and 5 are associates, right? Because there's a unit that times to each other. So we have a certain unique factorization up to like our wanting definition of unique. And yeah, an important equivalent characterization that was in the lecture is that if R is an integral domain, R is a UFD if and only if UD1. So UD1 is this axiom, by the way. Oh, not axiom, this property. If only if UD1 holds, and as well as that every irreducible element is prime. Yes, so we have that every irreducible element is prime in a UFD. Yeah. So yeah, an example question, 21 does not factor uniquely as a product of irreducibles in Z square root negative 5. So yeah, we have that 21 is equal to 7 times 3, but it's also equal to 4 plus square root negative 5 times 4 minus square root negative 5. And we have to show, it suffices to show that each of these factors are irreducible, right? So we take the case when it's 7. So if 7 wasn't irreducible, we would be able to write it as a product of a plus b square root negative 5, and so on. We take the complex normal of both sides, and we get that 49 has to be a squared plus 5b squared and c squared times c squared plus 5d squared. 49, has only divisors 1, 7, 49. So we can just exhaust the cases, right? If a squared plus 5b squared equals 1, then we have a is plus 1 and it's 1, or b is 0, which is a unit, right? In this case, we're trying to prove that, we're assuming these are both not units, right? Because if those units, they don't satisfy the irreducible definition. Same thing for c squared plus 5d squared. So we know they both have to be 7, but again, like you can see, they're both square numbers, they're both positive, you can't get 7, right? Yeah, so yeah, you can basically extend this approach to the other 3 factors to show that they're all irreducible. As in like 7, 3, and all of these are irreducible. Yes, so, okay, Jeff already talked about principal ideal domain, but yeah, again, a principal ideal domain is if every ideal is principal, and principal means that it's generated by one element, right? So like, every ideal is of the form with one element generating it. And again, we're not going to prove these because we don't have time, but there was in the lectures you were able to prove that for a principal ideal domain, every irreducible element is prime, and every non-zero non-unit element R could be factored into a product of irreducible elements, right? So with these two, remember the the other equivalent characterization that we had? Yeah, this equivalent characterization. This would imply that a PID is actually UFD, right? So that's a very important inclusion that we actually have. Yep. And we also did show, well, Jeff mentioned why ZX is not a PID, but yeah, a rigorous proof would be that you can consider the ideal generated by 2 and x, right? So suppose that I is principal, then there exists some alpha such that that generates the whole thing. This means that alpha must divide 2 and alpha must divide x, right? Because 2 and x would be in the ideal. But if alpha divides 2, then alpha is either plus minus 1 or plus minus 2. If alpha is negative 2 or 2, then it doesn't divide x, so alpha is plus minus 1. But if plus minus 1 is in the ideal, then obviously everything is in the ideal, right? So it generates the entire ring. But 3 doesn't divide 2 and x, so 2 and x is not the entire ring. Any questions? No. Okay, and then we get to Euclidean domain, right? So the intuition behind Euclidean domain is essentially like we want to do Euclidean algorithm on our ring. And I find it always like, I find it nice if you always like use your intuition for integers and move it over to every ring result. So like in integers, if you remember, then like Euclidean algorithm goes like what? Like you have 2 integers a and b, right? You start with 2 integers a and b. If like you do the algorithm, one of the cases would be like if a or b is equal to 0, then we have to stop. And like the non-zero number is the GCD, right? Of the 2 numbers that we start with originally. otherwise, if A and B are not, if none of them are equal to 0, then we can assume that one of them has a bigger absolute value. And then we're able to take a division of it such that the absolute value of R is less than the absolute value of B. And then we did the algorithm again with the pair where you replace A with the R, right? And you can keep doing this and it terminates at some certain point. If you see why this is true, the key thing is the absolute value function. The absolute value function is what makes us be able to do this algorithm and terminate at some point. And what the key property of this absolute value function that we need is that the absolute value function, it outputs non-negative values, right? So the absolute value function outputs non-negative values. And another property is that for any numbers A and B, we're able to find something which is like, we're able to find some sort of Q, right? Such that A minus QB, the absolute value of A minus QB is a smaller absolute value than B, for example, right? That's essentially the key properties of what you want so that the Euclidean algorithm works, right? And basically, you just convert that over into your axioms. So a Euclidean domain is literally just a function which satisfies literally the two things I just said, i.e. that you have that, what do you call it? You have that like there always exists some Q and R in D such that f is equal to GQ plus R, where the absolute value in a certain sense is less than f of G. And this is essentially the same as saying that it outputs non-negative values. If such a function exists, then we call that D a Euclidean domain, right? So it turns out that every Euclidean domain is a principal ideal domain. I think I have enough time to prove that. So like if we have a Euclidean domain and we have some sort of ideal, right? If it's the ideal, which is just a zero ideal, it's trivial, so we don't care, right? So we'll choose some sort of element P inside this ideal, which is non-zero, right? And the whole idea that we can prove it's a principal ideal domain, it's actually quite simple using the idea that a Euclidean domain was literally made so we can do the Euclidean algorithm. So P is in the ideal I, P is non-zero. Let's say we have another element R in I, right? Then by the axiom, we have that we can have there exists some sort of elements. What did I say? Q and S in R, such that S is equal to R minus PQ, with the fact that V of S is less than V of R, right? But if we have this, then notice that R is an I, and we also have P is an I, so S would be an I, right? And we have V of S is less than V of R, so I mean V of, this should be V of, oh wait, it should, okay, we should have solved these two actually. It should be R and P. So the whole point is that we could choose this R to be the V which has the minimal value, right? But this is a contradiction, as if you have a minimal value, it would keep going down and down. So R would have to be 0. So it has to be generated by only one element. Yes, that was a lot. That was all over the place, but that is generally the idea. It's on the lectures as well. Yep. So yeah, some facts. Again, we can apply the Euclidean algorithm to find the greatest common divisor. Yeah. Another mention is that the greatest common divisor, it should have been in a problem set 8, I think, that all UFDs, there is a notion of getting a greatest common divisor. And we just proved that Euclidean domains are part of principal ideal domains, which are also part of uniquely factorizable domains. So it makes sense to think of a GCD as well, right? And this is also a question in the problem set, which was that we want to show that this quadratic integer ring is a Euclidean domain, right? And so it uses the same proof similar to lectures, so I'll go pretty quick. But yeah, like proving the first axiom is pretty clear, as we have that this function nu is actually a norm, right? So we already have that. This is sort of true. And to prove the second property, we use the same idea where you think of the lattice points which are formed by our quadratic ring. And these have distance 1 between each point, but this has distance root 2, right? If you think of all the points which are formed by a plus b square root of negative 2. Or this is a plus b, you can think of it as a plus b square root of I, right? So if you think about like which points are formed, then you have a lattice where every horizontal distance would be 1 and every vertical distance would be root of 2. So we have that r equals pq plus s. We want to choose some sort of q bar, which is a lattice point, but we want to choose it so it's as close by most root 3 on 2. And it's the same idea as the lectures where you had, like, if r on p is a point of a complex number and exists somewhere in one of these lattice boxes, because there's 4 corners to the lattice box, you can divide into 4 regions. You have one of those points which is at most root 3 on 2 close because you'll be at most this distance close, right? Which comes to be root 3 on 2. And so we just use the same thing where we substitute that in, and we get 3 on 4 p squared, which is less than b, which is nu p is less than nu p is greater than nu of s. Yeah, yeah, pretty simple. It should be the same proof. Yeah, and another example of a Euclidean domain is if k is a field, then k of x is a Euclidean domain. Yeah, this is essentially just the division algorithm that we like to do with our polynomials, right? Where the function that we care about now is degree of p, as in the thing that keeps going down and keeps telling us, oh, like it's our remainder in a certain sense. Yep, so is z of square root of -5 a Euclidean domain? No, because we already showed before that 21 did not factor uniquely, right? So if it doesn't factor uniquely, then it's not a UFD. And if it's not a UFD, then it's not a Euclidean domain. So that's a simple proof that you can show. And yeah, the astute would notice that like the proof here, there's a certain point where it fails, and it should be mentioned on the problem set as well, actually, that this fails at this same template of a proof fails when it's z of square root of -3. Yeah. Nice. Okay, Gauss's lemma. So yeah, we first define polynomial to be primitive if the coefficients are all co-prime. Yeah, this also makes sense because we're right now talking in UFDs. So yeah, that makes sense that a function, polynomial is primitive if all the coefficients are co-prime, as in the greatest common divisor is 1, right? Then a lot of the lemmas are skipped for the Gauss lemma in this one, because the lecture slides there's a lot more lemmas and propositions which build up to proof. But we have these two which are pretty important, I would say. And it's that if we have a UFD, and suppose that f and g are primitive polynomials in the polynomial ring, then fg is also primitive. And we also have that if R is a UFD and k is its fraction field, then every polynomial in the polynomial ring over k has a decomposition where f is equal to lambda g, where lambda is the k, the invertibles in the field, and g is in the polynomial ring over R, and it's primitive. So a good intuition for that is just like think about it in the case where it's think about in the case where R is z, then like your k would just be q. Essentially, it's just saying like if you have any polynomial f in like q of x, you can sort of take away as much of the fractions as you want, and then you're left with integers, right? But you only leave the integers so that you only leave enough integers so that it's primitive. If you leave more, common factors, then it wouldn't be primitive because there's a common factor, right? Does that make sense? Yeah. Yeah, hopefully that makes sense. And yeah, this decomposition is unique up to multiplying by lambda by u and g by u inverse where u is a unit. And if f is in R of x, then we have that lambda is in R. Yeah. So I'll omit the proof, but the proofs are all in the lectures, obviously. So yeah, you should probably. But this Gauss's lemma too, I think you've seen it more being used in problems, so it might be more important. again considered some uniquely factorizable domain. We have that irreducible elements in R of X are irreducible elements of R, obviously, or they correspond with primitive polynomials, so primitive in R of X of positive degree, which are irreducible in K of X. So essentially it's saying like us trying to factor in K of X is essentially the same as trying to factor in R of X, as long as we're only thinking of primitives. Because we don't really need to care about the ones which aren't primitives, because of this proposition here before, we were able to take out as much with the lambda to make G be primitive, right? So we don't really care about polynomials which aren't primitive. So essentially, Gauss's lemma 2 states that knowing a polynomial which is like factoring a polynomial in R of X is essentially the same as factoring a polynomial in K of X. And yeah, furthermore, we have every irreducible element is prime. So using these, we have a result that if R is a UFD, then R of X is a UFD. And I think it states in the lectures that you can obviously inductively just show that R adjoining anything is a UFD as well, right? Any number of things, finite number of things, I guess. So why? I wrote a short like proof, but essentially, like, okay, I'll write it out because I have it. But essentially, if we can show that, so if f is in R of X, we want to show it can be uniquely factorized, right? So we need a certain unit. We need to construct a unique factorization. By the lemma, we can have f be lambda g, where lambda is in R and g is primitive first, right? So by one of the lemmas we have up here, we can, as I said, like the intuition is you just take away the factors. We can factor out a lambda and ring to make G be primitive, right? So we take out all the common factors. G is still in X. Right? Now, what we can do with G is that since G is primitive and is in R of X, we can factor it. We can think of G living in K of X, right? And we can factor out because K of X is K is a field, so K of X is always going to be a UFD because we said K of X is already, we said for every field K of X is a Euclidean domain, right? And remember the chain, so K of X is obviously UFD. So we can factor G into a product of irreducibles where each of these are in K of X. Whoa. Yes, K of X, right? Now, what we want is that we now want it to go back into R of X. And so we can use our lemma again, and we can say that we can find some sort of polynomial T of I, which is equal to AI times GI, where AI is in the fraction field, GI is irreducible in this, but then PI is now, PI is in PI is in R of X, right? So like, yeah, this is possible by, again, one of the lemmas that you can always find. But if you have this now, then that means we can represent this now as like a product of lambda, A1 inverse, A2 inverse, and so on, AN inverse, and a product of PIs, where notice that if G of I is irreducible, and we've only multiplied by some sort of unit in K, P of I will still obviously be irreducible. So we have a bunch of irreducibles which live in R of X. So these are all products of irreducibles. Again, by the lemma above, this will also be like these are products of. Oh, we also want P of I to be primitive still, I think. No, P of I we want to be irreducible. So this is fine, I think. We keep it like that because we have a product of irreducibles. Now we have something that lives potentially in K. Yes. No, I think we still want P of I to be primitive. So we'll choose an A of I such that P of I is still primitive. And that means this is a product of primitive things, so it'll still be primitive as well. Yeah. And again, by the lemma above, it has that if we have some sort of polynomial f which is an R of x, which is written as like something times in the unit of the fraction field times a primitive polynomial, then this has to be an R. So yeah, we have some sort of decomposition now where f is written as something in R times a bunch of primitives or irreducibles in R of x. And now we can factor out R because R was by assumption UFD. So that's basically the gist of the proof. And then you still have to prove that this factorization is unique. But I'll refer you to the lecture notes to find that. Yeah, it's not that hard from here. Yeah. So yeah, a problem set 9, question 9 example. Prove that cos pi 9 is a root of this. So yeah, first part, to show that it is a root, you can just consider the identity cos 3x, right? Yeah, cos pi 3 is a half. So yeah, it works. And so now using Gauss's lemma, if we want to prove irreducibility over Q of x, we have that, as you can see, this f is primitive over z of x, right? Because z is the UFD that we care about, where the fraction field of this turns into Q. So yeah, this is primitive over z of x. And so by Gauss's lemma, proving that this is irreducible over Q of x is equivalent to proving it's irreducible over z of x. And we just need to work over z of x now, and the degree is odd, right? So if the degree is odd, we must have a linear root if it is reducible. And that means if the linear root looks like ax plus b, we must have that a divides a and b divides -1, right? If you look at the factorization. But then that means the root will be of the form like plus minus 1, plus minus 1 on 2, plus minus 1 on 4, plus minus 1 on 8, right? Everybody agree with that? Yeah? Because the root would be negative b on, well, it wouldn't be negative b on a, but it would be something that divides b, something that divides on a. So we get the roots have to be one of these 8, but I wrote that you can check that none of these work. Yeah, I did check it. It's on my paper, so yeah, you can just trust me with that. Yes. So yeah, okay. Now we get to fields and their extensions. So, yes, a field is a ring, and we recall that a ring has a bunch of this. But for R to be a field, we require that R contains a multiplicative identity. We already assumed that. R is commutative under multiplication, so it's a commutative ring. And every element in R has a multiplicative inverse. So yeah, like a shorthand slogan for this is just a field is a commutative ring. Is a commutative ring where all non-zero elements are units. Say division ring. Oh yeah, sure. Yeah. Yeah, sure. Yeah. Essentially, it's not that complicated. It's just you take a commutative ring and you make sure that everything can be inverted, right? So yes. We go straight away into extensions of a field. And the idea is, yeah, we have a field, and the question is asking like, what happens if I want to add new elements into this field, right? So like we want to formalize this notion. So we have, if this is the inclusion of fields, f and e be fields. If E is a field, then we call E an extension field of F. That's essentially, the definition is pretty simple for extension fields. But we also write like EF is a field extension. Yeah, it's all just definitions and notations, nothing complicated there. But this is important, I guess, because if we have alpha 1, alpha 2, all the way up to alpha n being in the bigger field E, then we write this notation that F, open bracket, all of the alphas, is the smallest subfield of E that contains F as well as all of these elements that we want. We also say an extension is simple if it is of the form where we only adjoin one element. Yeah, so yeah, notice that, we have to define again. So yeah, same setup, E is a field extension of F. We have some element alpha in E. we say alpha is algebraic if alpha is a root of some polynomial p with coefficients in f. So yeah, like to make this more like from the lectures, right? You remember that like we have a certain map that we can define, like to motivate the definition of this. To motivate the definition of this, hopefully you remember that we have some sort of map that we can define from the polynomial ring over over f to E, where we essentially just map, we substitute alpha in for x, right? We said that this has like, okay, well clearly, first of all, we want to look at the kernel of this map, right? And what it means to be algebraic and what it means to be transcendental is essentially matching to the cases of whether this kernel is trivial or not trivial. So if we look at the kernel of this map, if it is trivial, then essentially means that none of the polynomials will turn into like anything that gives us E. So like in this case, it matches the definition that like alpha is said to be transcendental. And in the other case that the kernel alpha is not trivial, like I don't know what to call this map, the kernel of the map. If the kernel of the map is non-trivial, we know that the kernel of the map is an ideal. We also know that a field is trivially a principal ideal, right? Principal ideal domain, because there's only two ideals. So the kernel of this would be generated by one polynomial, which we call the minimal polynomial. And this minimal polynomial will have the minimal degree. That's why we say alpha is algebraic if alpha is a root of some polynomial p, where this polynomial p is the one with minimal degree. Yes. Yeah, we call this the minimal polynomial. Those properties and those proofs that you can show that this minimal polynomial is irreducible, right? So yeah, we can't split it, essentially. We can't keep splitting it. Yeah, the proof is, you can find it, it's pretty easy. If you split it, then obviously you would have another smaller polynomial with smaller degree. And we have that if E is equal to the field extension, the simple field extension of alpha, if alpha is algebraic over F with minimal polynomial P, then we have that E is equal to F just adjoining alpha, actually, like adjoining alpha in the normal sense, which is isomorphic to the quotienting of the ideal. And if alpha is transcendental over F, then E is isomorphic to f of x, following the universal property of fraction fields. I think I'll omit this, but like, okay, well, I think we'll cover this. We have that, so if alpha is algebraic over F, right? We have that, we'll have that P is irreducible by our previous dot point. And if P is irreducible, we have that this implies that the ideal of P is maximal in a principal ideal domain. Under the settings that we're working in a principal ideal domain, if P is irreducible, then the ideal generated by P is maximal. This gets used quite a lot, so I'll just mention it. And if the ideal generated by P is maximal, then we have that quotienting by it is a field, right? Did you mention this, Jeff? Yeah. Yeah, as Jeff has mentioned. So if this is a field, then you have that this is a field which contains alpha and also contains f. But f of f, the simple extension was defined as the smallest field containing f and alpha. So we have that in this case that simple extension is equal to the extension adjoining alpha, which is isomorphic by the first isomorphism theorem to this. The second one, you don't need to know, I feel like. We won't ever get tested on the universal property of fraction fields. But for the ones who are curious, you can go read it. The universal properties are amazing. So I really want to show it, but I won't show it because it won't get used. But I do know it, but I won't get show it. It's in the problem set 7, I think, from my memory. So yeah, just like go and find it. Yeah. So this motivates us to know which polynomials are irreducible and like which like trying to find out like what the minimal polynomial is essentially trying to find out what polynomials are irreducible and when they are, right? As like mentioned in the lectures by Alex, you can use Gauss's lemma. That's one way to show, like, to have a technique of trying to find which polynomials are irreducible. But another one that's important is Eisenstein's criterion, right? And yeah, Eisenstein's criterion states that, yeah, hopefully everyone knows, like, it's very important. It's just like if you have a polynomial in R of x, then suppose there exists some sort of prime that divides the first n coefficients, but doesn't divide the very last biggest degree, and you have that the prime squared doesn't divide the very first one, then we can conclude that f is irreducible over the fraction field. Yes, so using that, we'll try and do this question in 2023. Find the minimal polynomial of alpha over q and prove that the polynomial is minimal. So just in the first attempt, we'll just try and find a polynomial for this, which alpha is a root of. So the most natural way to do that would just be like, high school algebra. You just square it, move it over. Yeah, we get a polynomial which alpha is a root of, right? So we'll just make a suitable guess that this might be the irreducible polynomial, like this might be the minimal polynomial. So we want to prove that it's irreducible then. And to prove that it's minimal, we use Eisenstein's criterion, as we said. You can see that 2 divides 14, 2 divides 10, but 2 does not divide 1, which is the leading one. But 4 doesn't divide 14, which is the one at the very end, like the constant factor. So yeah, this meets all the criteria, of Eisenstein's criterion. So we can conclude that the polynomial is irreducible and therefore minimal. Does that make sense? Another usage was also in the 2 to 10 for question 7. This one, you have to notice, it's quite nice, but it's also quite simple using Eisenstein's criterion. And it's the fact that we first have that f is primitive. So I should maybe rearrange the sentence to say that first f, which is defined as, is the fraction field of, this is the fraction field, right? So f is the fraction field of fp of x. And we have that f is primitive over the field fp of x. So by Gauss's lemma, it suffices, like, that means we can use Gauss's lemma to prove that f is irreducible over the field before the fraction field. Does that make sense? So like, fraction field is when it's k, before the fraction field is r. In this case, now we can use Gauss's lemma to instead now try and prove that f is irreducible over, oh wait, what am I writing? This should be r and this should be k, like what I'm pointing at. It suffices to prove that f is irreducible over this polynomial ring, I guess. But yeah, we clearly have that, like, that means we can choose x as a sort of like element of the field. And it means that x divides, obviously, the constant factor, but it doesn't divide 1 at the front. And we also have x squared doesn't divide x, right? So by Eisenstein, we can conclude that f is irreducible. Does that make sense? Okay. So yeah, a very important like shift in perspective is that if we have a, I forgot to edit here. Like, apparently I had a complaint that the field extension is always written like this. So yeah, my bad. So if we have a field extension E/F, then we can always view E as a vector space over F, with the degree of the extension, well, that's the definition of what we're going to say. We're going to define the degree of the extension as the dimension of F over VE, E over F. Yes. This is very important. This is like, now suppose that alpha is algebraic over some field F. Is this one correct now? What this? Okay, yeah. Now suppose that alpha is algebraic over some field F, then the degree of the extension field F of alpha over F is precisely the degree of the minimal polynomial. So this is it is non-trivial. You still got to prove this. So you want to, I will redirect you to the lecture slides for you to find the proof of that. But the dimension, so it turns out that this is quite amazing actually, but I have to skip it because of time. The dimension of f alpha over f, so just simply adjoining alpha over f, this dimension as a vector space is equal to the degree of the minimal polynomial. And yeah, I redirect you for the proof. But the idea is like if the degree of p, yeah, if degree of p is like n, for example, then the idea is that like you can have 1x, x squared, all the way up to x to the n minus 1. These are all like linearly independent vectors over the vector space, over the vector space f alpha over f. So like none of these can be equal to 0. If they were equal to 0, then your minimal polynomial would have a degree that's less than n. So like, yeah, if that doesn't make sense, that means you didn't read the slides. So go read the slides. In fact, so we can construct the tower of extensions. So we have, again, field extensions that tower like this. And this is like synonymous to like Lagrange's theorem, right? I should mention that apparently in Galois theory, they are apparently the same, which I have no clue because I don't know Galois theory. But the proof of this is actually very nice. Like the proof of this is like you can prove this if you prove this previous result, which you know that the degree of the minimal polynomial is the dimension, like these two are the same, then like you can work basically fully over the vector spaces, and you can take a basis for this one, and you can construct the basis which there's like m times n many elements in that basis, and you can prove that they are a basis, and you can prove that it's spanning. That's essentially the whole proof. But the whole proof, what I'm saying is that it's actually very nice because you can prove something in linear algebra, and linear algebra is usually very easier, like it's much easier for us to work with. So, yes, yeah. As a note, as for my previous example, since we showed that the minimal polynomial of cos power 9 is x cubed minus 6x minus 1, because we showed it was irreducible, we can conclude that the extension would be 3. So yeah, that's just a quick statement. And we can try another question. So let p be greater or equal to 3, and let theta be 1 plus a sum of these like pth roots. These are all like pth roots of p to the power of some sort of odd power, right? 2i plus 1. Yeah. And so we want to find the field, like the degree, right? The extension. The degree of this extension. That's what the question asks for. And so, yeah, we can observe that Q is a subfield of this, and this is also a subfield of this because we can see that if we have a field containing root, like pth root of p, that pth root of p can always make this phi, right? Because this pth root of p is just essentially like a sum of like 1 plus a plus a cubed plus a to the power of 2p, like a5 all the way up to a2p so on. So since any field that contains the pth root of p can make theta, we can make everything in here using a bunch of these like pth roots of p. So we can see it's a subfield. And so by the Taylor extension, we have that like we would have that like this. We can express this ratio as this times another thing, right? Which is an integer. So that's why it divides. And by Eisenstein's criterion, we can claim that this has minimal polynomial x to the p minus p. So I'll skip the details of that. It's a minimal polynomial. And so if this is the minimum polynomial, then we know this has to be p, right? Oh, and I didn't even mention that it's prime. My bad. And you'd probably be angry, but yes. Yeah, so we have that this field extension divides the prime p, and that means it has to be either 1 or p. And it doesn't make sense if it's 1, because if it's 1, retrace your definitions. If it's 1, then that means theta can be written as like, that means the degree, like theta is the degree, a root of a polynomial which has degree 1, which means that theta can be written as like some sort of element in Q. But as you can see in this case, it's actually not obvious, but well, in this case, theta is not rational. So does that make sense? So we know it has to be P. Yes. So going on that, we have a very natural notion of what a splitting field is then. So yeah, if you have a polynomial and if we consider this polynomial over Q, then we can see it's irreducible, right? But again, we can add on some certain things such that f can be factored into these linear factors, right? That's essentially the whole idea of splitting field, is that we want to have some sort of field, and we want to keep adding on elements such that f can be split into linear factors. So the next slides are literally just making those formal. So if f is a field, a splitting field of some polynomial is an extension field such that p splits into linear factors. And we generally, so I'll go to this next slide. It should be defined in the lectures that we have this theorem by Kronecker that there always exists a finite field extension such that f is a product of linear factors. And he does this sort of inductively, where you take like the polynomial, you take an irreducible factor, you add in a root, and you essentially continue this until you've had all the roots, right? And he defined that as the splitting field, because as you can see, splitting fields, if you define a splitting field as any field which splits, then you can have larger fields which really don't care about the other parts, right? So yeah, we define the splitting field as the smallest field, which follows from the construction of Kronecker's, like Kronecker's proofs. It's Kronecker's proof, essentially. You can, again, see the lectures for that, for the more details of it. But let's try a question to make this sort of make sense, or have like a touch over it. X cubed minus 11 over q. So we want to find the splitting field of this polynomial. And recall that, like, if we want to find the splitting field, we want to factor it into linear factors, right? So we have that the roots of this f are clearly like these numbers, right? Where this is like this is a root of this is like the root to like x squared plus x plus 1, right? So as you can see, then here in this case, the splitting field becomes the cube root of 11 and adjoin that primitive root. Like it was in the proof of the Kroneckers, but essentially the idea is like you add on cube root of 11, and after you add on cube root of 11, any linear sort of combination of it we shouldn't really care about. And we know that this is, in a certain sense, like it still can't be made over q. It still can't be. We note that this can't be made over this. Essentially, that's why we add on that root again to adjoining it. To determine its degree, yeah, we can compute the tau of extensions as before, but as you can see, it's pretty straightforward, right? That will be degree 3, that will be degree 2, because of x squared plus x plus 1. So we get that it's 2 times 3, so it's 6. Does that make sense? Okay, moving on to the last part, basically. So, actually, I'm going quite fast. So, we have to go into the topic of finite fields. So yeah, we call f a finite field if it has finitely many elements. Wow. And then we know that any field must have characteristic 0 or prime, right? So in the lectures you should have seen, I can't quite recall what the proof of that was. Characteristic polynomial. No, I'm just trying to see why the characteristic has to be 0 or prime. I think it was like you took some sort of map, I think. But anyway. Right, yes, there's no zero divisor. Okay, yeah, so it's like if the characteristic wasn't prime, then you would have to, like, say the characteristic wasn't prime, then you have like some n, which is like n characteristic, which is a composite number, rs. You can take r times s, where r, s are actually in the field now. So r times s would be equal to 0, but then that means r and s are zero divisors. So yeah, we want them to be definitely prime. So yeah, so it's either 0 or prime. And then for finite fields, for finite fields, the formula can't hold true, right? Like if characteristic 0, then we don't have finitely many elements. So, so in the other case where if f is a finite field with prime characteristic p, then we have that f contains f of p, right? That's pretty obvious. It just like if you just look at the elements 0, 1, 2, 3, all the way up to like p minus 1, then that is, it contains f of p as a field. And so we also have that n is equal to, if we set n to be the the degree of the field extension of f and f of p, then we have that the cardinality of f is p to the n. Because if the degree of the extension is n, then again, like think of it as a vector space, you'd have like these as the vectors, which are linearly independent, essentially. And if you have these as the vectors, well, I don't know why I put x and x squared. They should be like a1, a2, and so on. But like, you have like a1, a2, an, which are all linearly independent. But then you have, since you're working over p, fp, you have like p choices for each of the coefficients. So it's just like you have p choices for the coefficients, you have n things for p to the power of n. That's why you have that many elements. Does that make sense? Yeah, right? Okay. Yeah. And so the important part which we care about is that let us say we have q which is equal to p to the n. If we consider if we consider x to the q minus x essentially, there exists a field extension by Kronecker which f splits into product of linear factors, right? If we take this certain set of f, which essentially is the roots of all roots to all of xq minus x, this is a field with exactly p to the n elements. Yeah, I'll redirect you to the lecture slides for that. But it should be shown that we can show that this is exactly a field with p to the n elements. And we also have a result that if two fields are both of order q, so p to the n, then they are isomorphic. So all the proofs are on the lecture slides for that. But the key importance of this is just that now then, there essentially is only one unique field that we care about of order p to the n. And I'll do this problem, which I thought was very important. In P set 9, the last question, if we have f be a monic irreducible polynomial of degree n, prove that fpn is the splitting field of f. So I've written a proof. So since f is irreducible and fp of x is a principal ideal domain, as we already, this is similar, we have that the ideal generated by f is maximal. And hence, this is a field, right? And this we note that again that this field, similar to all the things that we've done before, is isomorphic to what is going on? Oh, crap. Okay, no. I don't. Yeah. I was using a text pen. I don't know how that works. We know again that this is isomorphic to. Oops. We know that this is isomorphic to this by first isomorphism theorem again. So we have that adjoining alpha, yeah, is a field right now, and due to the max degree over this field right now, again, like f has degree, let's say f has degree n. I think that's a bad choice. Yeah, f has degree n, right? Then due to the max degree being less than n, with p choices again as a vector space, we have that the cardinality of k would be p to the n, right? And again, by result before, we have that then k is isomorphic to fp of n, because all of them are, all fields with p to the n elements are isomorphic. So now it just reduces to proving that it's a splitting field of f. And to show that it's a splitting field of f, we just need to show that like we adjoined one root where alpha, you can think of it as like x plus the ideal of f. Clearly, we have at least one root inside this field extension. We just need to show that after adjoining one root, if it is the splitting field, which is the smallest field, which has all the roots, we want to show that fp of alpha does have all the roots, right? So we have a lemma in the lectures, which was on the same page as this, lecture 32, I think. We have that this f must divide x to the q minus x. It was the lemma literally states as if m in fp of x is irreducible, then the degree is equal to n, then m divides x to the qx minus x, where q is equal to p to the n. So this is by a lemma in the lectures, which implies that all roots of f are also roots of x to the q minus x. We have that k has q elements, which means that the units of the field, so as in like you just get rid of 0, the group of that field has q minus 1. So this implies that all roots all elements of k are roots to xq minus x, because like by Lagrange's we have that like any element alpha, or not alpha, I already used alpha. All elements C in this group, we would have that C to the Q minus 1 has to be equal to 1, right? So C to the Q is equal to C. So C to the Q minus C equals 0. So all elements of K times are roots of x to the Q minus x. Since x to the Q minus x has the most Q roots, we can see that K are all the roots of that polynomial. And we had that F, all roots of F are all roots of F are all roots of K. And since all roots of F are in Fp of alpha, we have that it is the splitting field. So you can also essentially know that any field extension made by quotienting out some sort of irreducible polynomial, it is going to be isomorphic to the splitting field of F, as well as the field that we know, which has p to the n elements. So if we show a question which does use that, 2020 final had this question where it says show that the rings are isomorphic, then this is just a simple application of that question before, where we need to show essentially just that if we show that x squared plus x plus 2 and x squared plus 2x plus 2 are both irreducible, then we know these are both going to be isomorphic to f3 squared, as in f9. So that's all we have to show essentially for this question after you know that theorem. And that's quite easy to show that they are irreducible, because if there's irreducible in this sense, just means that it has no roots at all, because if it wasn't irreducible, then it would factor as a linear factors, right? And you just have to check all the elements, 0, 1, and 2. Yeah. So simple computation shows that both of these polynomials are irreducible, and so both are finite fields of order 9, and hence they must be isomorphic. Does that make sense? Yeah. Yeah. So we'll finish off with 2 finite field questions, and then we'll probably just, I guess, go into questions. But yeah, that's essentially the end. So this question says, consider the following rings, each of which has 9 elements. Sort these rings into equivalence classes. We have enough time. Should we try and make everybody else try it? You can see, okay, so first we can see that we can look at x squared plus 1, and we can see that x squared plus 1 is irreducible again in a similar manner, right? So already we can see that this is going to be isomorphic to f9. So we know these two are under the same isomorphism class. F3, z times 9z is not even a, this is not even a field, right? Not a field. Yes, it's not even a field. So we don't care, like this is obviously going to be on its own, separate to f9 and f3x squared plus 1. I think we can say the same with f3 times 3. But following the solution again, to understand the structure of this one now, so the very last one, we can see that its kernel can be made using this sort of map where this has kernel x squared minus 1 because any polynomial which has roots 2 and 1, like in mod 3, this is the same as this. And so we see that this is the minimal polynomial for polynomials which have roots 1 and 2. And so if for this to have kernel, it has to be obviously the ideal generated by x squared minus 1. So yeah, by first isomorphism theorem, we have this isomorphism from f3x quotient out that with f3 times f3, right? And f3 times f3 being like the image, because we can make everything, right? We can trivially make everything in f3 times f3. We just can use the constant polynomials if you want. So we have that these two are now under one equivalence class. So all that's left to look at is, I guess, this one, right? And like, I guess compare them with the other ones. So yeah, this is already mentioned that this is not even a field, so it has to be on its own. And we care about f3 quotient at x squared. And the idea for this one is that you can notice that it possesses a non-zero nilpotent element x. So like x in f3 of is nilpotent because if you square it, it goes to 0. It's nilpotent with order 2, But other rings, the only thing that's true is of Z9 of Z9Z, right? But Z9Z does not have an element with, but this one doesn't have an element of order 9. So we know these two have to be unique on its own. These have to be separate from each other. We have these two must be together, and we have these two must be together. We know that F3 times F3 is, it's not even a, it's not a field, right? Yeah, it's not a field, because you don't have the inverse for 0, 1. Because the identity would be 1, 1, right? If it was a field. So yeah. So each of these are in its own isomorphism class, like this. Yeah. Yep, and one final question is, this is actually the opposite of, I think it was shown in the lectures that if, I think the converse was shown, where if alpha and beta are algebraic over Q, then prove that alpha plus beta and alpha times beta are algebraic. So that was shown in the lectures, but this is a question where it shows the converse. So let's assume that alpha plus beta and alpha beta are algebraic. Then we have that this is finite, right? And by definition. And since these are algebraic, now we can consider this polynomial. This polynomial is now allowed to be in this polynomial ring because it has coefficients. And we also note that alpha plus beta minus alpha is beta. So the field extensions, these two field extensions should be exactly the same, right? So hence we can conclude that like adjoining these two on, quotienting out alpha plus beta and alpha beta is at most 2 because of our, we've constructed a polynomial where the degree is 2 and it's the roots, right? We don't know if it's minimal, that's why it's at most 2. And so like all you need to show though is algebraic. So, and by the Taube extensions, we then have that this is finite. Hopefully you guys can see that because this is going to be, this can be written as the product like this. This, I'm not bothered, but yeah, like everybody knows what I'm going to try to write. For beta, so long, but oh, you can't? Oh yes, thank you. And then you multiply the same thing, quotient Q. Right. We know these two are finite, so timesing is still finite. So we have that this is finite. And so we can conclude that suitably, this is I think the cool thing where you can now conclude that alpha and beta are algebraic because you can go in a different order. As in, you can also think of now, you can use the Taube extension where now you think of the field where you added alpha in first, and then you have the result. Yep. Another way you can also think about it is actually like this being finite already shows that like alpha is like you can again use the same like you can use the same definition where like if this is defined as a field extension where it's a polynomial which has all the like which has it'll be a product of polynomials which has all the roots, right? And the polynomial is finite, like the degree is finite because the extension is finite. But then that means like alpha, like just the minimal polynomial for alpha would obviously have a degree which is finite as well. So that's another way to think about it as well. Or you can think of it in terms of the vector space as well. You can think of it in terms of vector space where you can have like this field extension on Q is finite, saying that there's a finite basis. And if there's a finite basis, then you can just restrict that vector space into the vector space which you really care about with Q and alpha being being included. So there's many ways to think about it, but I feel like yeah, that's probably the great tool of knowing that the degree of the minimal polynomial is the same as like the field extension as a vector space. The dimension of the field extension as a vector space, yeah. So yeah, that's it. Any questions? No? I think we can end it there then. Yeah. Thank you for coming. Yeah, I think we can end the recording then. Oh yeah, I forgot about that.
Okay. Some closing remarks. Can we get a round of applause again for Jeff and Daniel for presenting, and also Justin, who's not here, who contributed to the slides. Of course, the obvious announcement to make is that we have a study day tomorrow. Feel free to drop in any time from 9 till 5 p.m. We'll probably be there later than that as well. Just around studying, we'll try to have a board tutorial type vibe, and people like Justin will be there to annoy you with questions, so it goes both ways. Yeah, so pop in. We'll try to have pizza there tomorrow as well. What our lovely treasurer can offer us will be there. Okay, so thank you all for listening. Yeah, best of luck for the final exam. Hope you enjoy this course. It is a lovely course, so take the time to appreciate all the beauty that is in this course compared to what you may have learned before. I think you all know what I mean by that. And yeah, thank you for listening. Those